From the smooth curve of a planet in its orbit to the seemingly endless flow of time, our universe looks like a perfect, continuous masterpiece. We experience reality as a smooth canvas, a stage where life unfolds without any jumps or jitters. We can move a tiny fraction of an inch or wait for a fraction of a second. There doesn't seem to be any limit to how finely we can slice up space, or how small a moment we can think about. This gut feeling that reality is infinitely divisible is baked into how we see the world. It's the foundation of classical physics, the bedrock on which Newton and even Einstein built their theories. But what if that's all an illusion? Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. What if, when you get down to the truly, unimaginably small, reality isn't smooth at all? What if the gorgeous, continuous fabric of the cosmos starts to fray? What if space and time themselves are made of tiny, indivisible pieces? Pixels of existence? Now, this isn't a question from some sci-fi movie. It's a question that sits right at the heart of modern physics, a deep mystery that pops up when our two best theories of reality go head to head. Today, we're taking a journey to the very edge of what's real, to a place where the world as we know it dissolves, and the fundamental rules of existence are just waiting to be found. We're going to ask one of the biggest questions out there: is our universe a perfect, smooth painting, or is it a breathtakingly high-resolution digital picture, built from a finite number of dots? The answer could change everything. The wall of the infinitesimal, the Planck length. Our journey begins with a simple act: zooming in. Imagine you have the most powerful microscope ever built. You point it at what looks like empty space and start magnifying. You zoom past dust motes, past bacteria, past the width of a human hair. Soon, you're in the realm of molecules, then individual atoms, their electrons buzzing around in a cloud of probability. You push even further, into the atomic nucleus, seeing the protons and neutrons inside. You keep going, diving past the quarks that make up those protons, into a realm of pure, empty space. Our intuition, and all of classical physics, tells us we can do this forever. Just like there's no smallest number between 0 and 1, you can always find 0, 1, 0, 01, 0, 001, and so on. We assume there's no smallest distance. Space, in this view, is a continuum. This is the world that Albert Einstein's general theory of relativity describes. It treats spacetime as a continuous, flexible fabric that bends and curves to create gravity. And on large scales, this theory works flawlessly. But as we keep zooming, we slam into the other pillar of modern physics, quantum mechanics. And this is where things get weird. Quantum mechanics is the science of the chunky. It tells us that energy isn't smooth, it comes in little packets, or quanta. An electron in an atom can't have just any energy, it has to occupy specific, discrete energy levels. It jumps between them without ever existing in the middle. For a long time, physicists just kept these two worlds separate. General relativity for the big, heavy stuff, quantum mechanics for the tiny, light stuff. But what happens when you need both at the same time? Like in the middle of a black hole, or at the very moment of the Big Bang? When you try to mix the smooth equations of relativity with the chunky rules of quantum mechanics, the math just breaks. The equations spit out nonsense, infinities. That's a giant red flag in physics. It doesn't mean the universe is infinite, it means our theory is broken. This breakdown happens at a specific, mind-bogglingly small scale, a fundamental boundary known as the Planck length. It's about 1/6 times 10 to the minus 35 meters. That number is so small it's almost meaningless. To give you some perspective, If you blew up a single atom to be the size of the entire known universe, the Planck length would be about as tall as a tree. This is the scale where gravity and quantum effects become equally strong, and where our physics stops making sense. So, why can't we just look at something smaller than the Planck length? Well, the problem is deep, and it's rooted in the laws of nature themselves. To see something really small, quantum mechanics says you have to hit it with a wave that has a really short wavelength. To probe smaller and smaller distances, you need more and more energy. And here's the kicker, courtesy of Einstein's E equals mc squared. Energy is mass. If you cram enough energy into a tiny enough space, you create mass. And if you cram enough mass into a tiny enough space, you know what you get. A black hole. The very act of trying to look at something as small as the Planck length would take so much energy that the area would collapse into a microscopic black hole, swallowing whatever you were trying to see. Nature itself seems to be telling us, this is a hard limit. It's a wall beyond which our ways of seeing fundamentally fail. The Planck length isn't just a tiny number. It's the frontier where our smooth, classical picture of spacetime shatters. It's the scale where the question, is space smooth or chunky, becomes a pressing scientific emergency. To go beyond this wall, we need a new theory, a theory of quantum gravity. And a lot of the best ideas suggest something radical, that our assumption of a smooth reality is the whole problem. The bubbling reality, quantum foam. So, what exactly happens down at the Planck scale? If we can't look at it directly, what do our theories predict? One of the wildest ideas was cooked up in 1955 by the brilliant physicist John Archibald Wheeler. And he gave it a name that's as cool as the concept itself, quantum foam. Wheeler suggested that if you could somehow zoom in on the fabric of spacetime, you wouldn't see a smooth, calm sheet. You'd see a roiling, chaotic, bubbling mess. He imagined spacetime at this scale as a foamy, constantly changing landscape where the very idea of geometry fluctuates violently because of quantum uncertainty. To get where this idea comes from, you have to know about one of the strangest parts of quantum mechanics, virtual particles. It turns out that even a perfect vacuum, what we think of as pure, empty space, isn't empty at all. It's a seething cauldron of activity. The Heisenberg uncertainty principle says you can borrow energy from the vacuum for incredibly short moments. This allows pairs of particles and their antimatter twins to spontaneously pop into existence from nothing, before almost instantly crashing into each other and disappearing. These fleeting little things are called virtual particles, and they are very real. Their effects have been measured with incredible precision in things like the magnetic properties of electrons. They are a constant, underlying hum of existence. Now, let's bring Einstein back. Relativity says energy curves spacetime. So what happens when you combine the two ideas? At our normal, everyday scale, the energy from these virtual particles is so tiny their gravitational effect is basically zero. But as you look at smaller and smaller regions of space, the uncertainty principle allows for more and more energetic particles to pop into existence. Down at the Planck length, the energy of these fluctuations becomes enormous, so big that they start to seriously warp and distort the spacetime around them. This is the origin of quantum foam. Think about the surface of a huge, calm ocean. From a satellite, it looks perfectly smooth. But as you get closer, you see waves. Zoom in more, and you see chaotic chop and spray. Quantum foam is the same idea, but for spacetime itself. What looks to us like a smooth, gently curving reality is, at its most basic level, a chaotic, frothing sea of quantum fluctuations. Tiny wormholes and microscopic black holes could be constantly blinking in and out of existence. It's a reality where space isn't just a static stage, but a dynamic, unpredictable player. The geometry of spacetime itself becomes a quantum object, subject to the same rules of probability as an electron. Now, we have to remember, quantum foam is still a theoretical idea. Experiments have been designed to look for it. One idea was that light traveling for billions of years from distant quasars might get blurred by this foaminess. So far, telescopes like NASA's Chandra and Fermi observatories have found spacetime to be, well, disappointingly smooth, at least down to scales 1,000 times smaller than an atom. But that doesn't mean the foam isn't there. The bubbles might just be too tiny for us to notice. And this isn't just a theory collecting dust. As recently as early 2026, scientists are proposing new ways to look for it, like a framework from Warwick University to detect foam using incredibly sensitive interferometers. Quantum foam is a powerful, if unproven, vision of what reality might be at its core. It paints a picture where the smooth canvas of existence dissolves into a chaotic, bubbling quantum mess. And it pushes physicists to wonder, if spacetime is this wild, maybe we shouldn't be trying to tame the foam. Maybe we need to replace the fabric altogether. Building blocks of the universe, theories of discrete spacetime. The idea that continuous spacetime breaks down has led physicists down a radical new path. If assuming reality is smooth leads to paradoxes, then maybe the assumption is just wrong. What if spacetime, just like matter, is made of fundamental, indivisible units? Just like the smooth look of water breaks down into H2O molecules, maybe the smoothness of space breaks down into atoms of spacetime. This is the core idea behind several leading theories of quantum gravity. Let's look at three of the most fascinating ones: loop quantum gravity, the Wolfram Physics Project, and causal set theory. Loop quantum gravity. Weaving the fabric of space. One of the most popular theories of a discrete universe is loop quantum gravity, or LQG. It takes Einstein's idea that gravity is spacetime geometry and it quantizes it. It asks, if every other force comes in discrete packets, why would gravity be different? LQG says that space isn't an empty void, it's a network, a fabric woven from a finite number of quantum threads. You can picture it as a cosmic web made of nodes and the lines connecting them, called a spin network. Each line, or loop, in this network represents a fundamental unit of area, about the size of the Planck area. These are the threads of space. Where the threads cross, they form nodes, and these nodes represent a fundamental chunk of volume, an atom of space. According to LQG, you can't have a smaller area or volume than these basic units. Space itself is grainy, and this network isn't in space, it is space. There's no in between the threads. Moving isn't a smooth glide from A to B, but a series of tiny jumps from one node to another. This whole structure is constantly changing, its connections reconfiguring. And that evolution, the change in the network's geometry, is what we experience on our scale as the curvature of spacetime and the force of gravity. The smooth fabric of Einstein's universe is just what you see when you zoom out from the pixelated quantum network. One of the best things about LQG is how it gets rid of those pesky infinities. Take black holes. In LQG, you can't have a singularity because you can't squeeze space down to an infinitely small point. There's a minimum volume. So, as a black hole collapses, it would hit a state of unimaginable, but finite, density called a Planck star. The gravity would then cause a quantum bounce, where the matter expands out again. This suggests that the center of a black hole might actually be a gateway to another part of the universe. In the same way, the Big Bang might not have been a beginning from an infinite point, but a big bounce from a previous, collapsing universe. But LQG isn't a finished theory. One of its biggest hurdles is proving that the smooth spacetime we see reliably emerges from this quantum network at large scales. Wolfram Physics Project, a universe of computation. A totally different, and more recent, idea comes from the Wolfram Physics Project, started by Stephen Wolfram. It begins with an even more basic question: what if the universe, at its core, is nothing but a simple computational process. The idea is that reality is an evolving hypergraph. Imagine a collection of points. Now, imagine a simple rule that says something like, whenever you see 3 points connected like this, replace them with 4 points connected like that. You start with a simple setup and just apply the rule over and over again. The Wolfram project has shown that these simple processes can create mind-boggling complexity. In this model, the hypergraph is the universe. The points are the fundamental bits of existence, and the connections between them create the structure of space. There's no pre-existing space for the graph to live in. Space is just the pattern of connections. Time isn't fundamental either. It's just the process of applying that rewriting rule, again and again, the act of computation itself. Every update is a tick of the cosmic clock. This leads to a wild conclusion. The universe is basically a computer, and the laws of physics are just the emergent consequences of its underlying program. What's amazing is that this simple model seems to naturally spit out features of our own physics without anyone programming them in. Researchers have found structures that act like particles and have shown how the large-scale behavior of the graph can be described by Einstein's equations. It even offers a new picture of quantum mechanics. Because there can be many ways to apply the rule at any given step, the universe doesn't follow one single path, but explores a branching web of all possible histories, which looks a lot like the quantum world. The idea that all the complexity we see could come from one simple rule is powerful. The project is still young, but as of early 2026, it's pushing forward, trying to explain everything from dark matter to quantum mechanics. Causal set theory, the primacy of order. A third approach, causal set theory, starts from a different place entirely. It says the most fundamental thing about spacetime isn't distance, but the relationship of cause and effect. The core idea is that spacetime is just a collection of discrete events, spacetime, atoms, and the only thing connecting them is the order in which they happen. Event A can cause event B, but B can never cause A. This creates an ordered list of events, called a causal set. Causal set theory says that this causal set is reality, and the smooth spacetime we see is just an approximation that emerges from it. The theory's slogan is basically, order plus number equals geometry. The order is the causal structure. And since the events are discrete, you can count them, that's the number. The theory suggests that just by counting the number of atoms in a region, you can define its volume, and from there, reconstruct all of geometry. The appeal of causal set theory is its beautiful simplicity. It strips reality down to its bare essentials, events and the causal links between them. It also cleverly handles a thorny issue in physics called Lorentz invariance, basically ensuring there's no preferred direction or speed in the universe. But it has its own problems. Mathematically, most of the causal sets you can create look nothing like our smooth, four-dimensional universe.
The big challenge is to show how and why the universe-like ones are the only ones that matter, leaving the bizarre ones behind. Each of these theories offers a unique and profound vision of a pixelated universe. They're all incomplete and face huge challenges, but they represent a massive shift in our thinking. They suggest the smooth world we see is just a low-resolution view of a much richer, stranger, and ultimately discrete reality. We've just been on a trip through the mind-bending frontiers of physics, from quantum loops to computational universes. And this is a conversation that's happening right now, with new discoveries and new ideas popping up all the time. If your mind is buzzing with these ideas like mine is, make sure to subscribe and hit that notification bell. We dive into questions like this every week, and you won't want to miss where we go next. A ton of research goes into making these deep topics accessible. If you want to support that work directly, think about joining our community on Patreon. Your support helps us keep exploring these incredible ideas. Now, let's get back to the cosmos. Implications of a pixelated universe. The idea of a discrete spacetime isn't just a game for physicists. If it's true, it would have huge consequences for how we understand the universe. It would force us to rewrite the stories of black holes and the Big Bang. So, what does it actually mean to live in a pixelated universe? Let's start with black holes. According to Einstein, when a massive star collapses, it crushes itself down to a point of zero volume and infinite density, a singularity. That's a point where our laws of physics just give up. And physicists have never been comfortable with that. A discrete spacetime changes everything. In a universe made of atoms, of space, you simply can't crush matter down to a point of zero volume. There's a minimum possible size. So, what happens instead? As matter falls into a black hole, it would be squeezed to an unbelievable degree, but it would bottom out when it hits the fundamental graininess of space. The center of a black hole wouldn't be a singularity, but a Planck core, an object with a stupendously large, but finite, density. The forces would become so strong they'd halt the collapse and cause the matter to bounce back. This quantum bounce could lead to some wild possibilities. One idea is that the bouncing matter could emerge somewhere else, maybe forming a new universe. In that picture, black holes could be cosmic mothers, giving birth to baby universes. Another idea is that this solves the famous black hole information paradox. Quantum mechanics says information can never be destroyed. But if you throw something into a classical black hole, its information seems to be lost forever. In a discrete universe, the information doesn't hit a dead end. It's stored in the Planck core. As the black hole evaporates over trillions of years, that information could be slowly released back into our universe, solving the paradox. Now let's rewind to the beginning of everything, the Big Bang. Just like with black holes, general relativity says our universe began as an infinitely hot, infinitely dense singularity. And again, a discrete spacetime offers a compelling alternative. If the universe has a minimum size, it couldn't have started from an infinitely small point. Instead, the Big Bang might have been a big bounce. Our universe could be part of an eternal cycle. A previous universe might have collapsed, shrinking down until it hit the fundamental Planck density, at which point a powerful quantum bounce triggered the expansion that we see as our Big Bang. In this picture, our beginning wasn't a beginning from nothing, but a transition from a previous cosmic era. Finally, what would a pixelated reality mean for reality itself? It would mean that on the deepest level, our universe is digital, not analog. Motion wouldn't be a smooth flow, but a series of discrete steps, like a character moving across a grid in a video game. These steps would be happening at the Planck time about 10 to the minus 43 seconds, so impossibly fast that they create a perfect illusion of smoothness. Time itself would tick. There would be a fundamental unit of time, the shortest possible interval. Nothing can happen in less than one Planck time. This also opens the door to tests we can actually perform. One popular idea is that the speed of light might not be perfectly constant. In some of these models, high-energy photons gamma rays might travel ever so slightly faster or slower than low-energy photons. Their tiny wavelengths would be more sensitive to the graininess of space-time, like a small wheel getting caught on tiny bumps that a large wheel would roll over. Astronomers are on the hunt for this effect, observing gamma-ray bursts from billions of light-years away. If high-energy photons from a burst arrive a little earlier or later than low-energy ones, it could be the first real evidence that spacetime is pixelated. So far, they haven't found anything, which puts some limits on these models, but the search continues. The implications are just staggering. A discrete universe is a computable universe. It replaces the confusing infinities of our current theories with the solid reality of a fundamental, grainy structure, changing our understanding of everything. The unfinished puzzle. So, after all that, where are we? We started with a simple question that challenges how we see everything. Is reality smooth, or is it grainy? We've traveled down to the Planck length, a fundamental wall where our best theories of physics just fall apart. There, we found the chaotic vision of quantum foam. This led us to the radical idea that the smoothness of reality is just a large-scale illusion, a trick of a fundamentally discrete, pixelated cosmos. We explored the spin networks of loop quantum gravity, which weave space from quantum threads. We dove into the Wolfram Physics Project, which pictures the universe as a giant computer running a simple program. And we considered causal set theory, which boils reality down to its bare essence, a chain of cause and effect. Each of these ideas, in its own way, gets rid of the paradoxes of a continuous universe and replaces them with the solid reality of fundamental building blocks. It changes how we think about black holes and the Big Bang, turning singularities into bounces and reframing the very nature of time. But we have to remember, we're standing at the edge of what we know. As of today, in early 2026, the question of whether spacetime is continuous or discrete is one of the biggest unsolved problems in science. These are competing ideas, not facts. We haven't found the definitive answer yet. The search for evidence, whether from the light of distant galaxies or from fantastically precise experiments right here on Earth, is one of the most exciting quests in all of science. This journey is more than just a scientific question, it's a profound shift in how we relate to the cosmos. It suggests that the universe, in its deepest workings, might be more like a digital computer than an analog clock. It hints that the richness of everything we see could be the result of simple rules playing out on a cosmic scale. The final answer isn't known, and the puzzle of reality is far from finished. But in asking the question, in daring to imagine a universe built from indivisible pieces, we're taking part in one of the grandest intellectual adventures in human history, the quest to read the fundamental source code of existence itself. And what we find there might be stranger, and more beautiful, than we can possibly imagine. The smallest possible length. Imagine taking a step closer to reality than anyone has ever stepped before. Not closer in the ordinary sense, not walking across a room or leaning in toward a screen, but closer in scale. Smaller. Deeper. Past skin, past cells, past molecules and atoms, past the restless haze of electrons, past the tiny crowded heart of the nucleus, and further still into a place where size begins to lose all familiarity. A place where the distances become so small that language itself starts to feel oversized. At first, it seems natural to believe that this journey could go on forever. If you draw a line on a page, you can always divide it again, and then again. Half becomes a quarter becomes an eighth, then a 16th, then smaller still. Our minds are comfortable with that idea. We assume that space, like a line in geometry, is infinitely divisible. No matter how tiny a distance becomes, there is always room for a smaller one hiding inside it. That assumption feels so obvious that most of us never stop to question it. But modern physics does question it. Quietly at first, and then with growing urgency. Because when physicists tried to combine our deepest theories of the universe, something strange began to appear. Not a neat answer, but a warning sign. A limit. A number so absurdly small that it almost feels invented, and yet it emerges from some of the most important constants in nature. This number is called the Planck length. And if it means what many physicists think it might mean, then space is not infinitely smooth after all. There may be a point beyond which the idea of distance itself begins to break apart. Tonight, we are going to stay with that idea for a while. We are going to slow down and sit beside one of the strangest possibilities in all of science. We will explore what the Planck length is, where it comes from, why it matters, and why some physicists believe it could be the closest thing the universe has to a smallest possible unit of space. And somewhere along the way, the world may begin to feel a little less continuous and a little more mysterious. If these slow journeys into the deep structure of reality help you relax, you can leave a like, subscribe to the channel, or share where you're listening from tonight. I always enjoy seeing how far these quiet questions travel. To begin, let us step back for a moment and ask a simpler question. What does it really mean for something to have a size? A grain of sand has a size. A cell has a size. An atom has a size, although not in the clean, solid way we once imagined. Even the atomic nucleus has a size. In daily life, size feels ordinary. It is one of the first things we learn as children. Big and small, near and far, wider, thinner, taller, shorter. But in physics, size is not just a description. It is tied to what can be measured, and that distinction matters. A distance only has meaning if, in principle, something could reveal it. Some interaction, some comparison, some physical process. If there were a region of reality so small that no experiment could ever probe it, then asking what exists inside that region might become less like science and more like poetry. That is exactly where the Planck length enters the picture. It is not simply the smallest thing anyone has seen. It is not a tiny particle floating somewhere in space. It is a scale built from three of the deepest constants in nature: the speed of light, the gravitational constant, and Planck's constant. Those three numbers belong to three enormous pillars of physics. The speed of light governs relativity, the structure of spacetime, and the ultimate speed limit of the universe. The gravitational constant governs gravity, mass, and the way matter curves spacetime. Planck's constant governs quantum mechanics, the strange granular rules of the microscopic world. When you combine these constants in the right way, something remarkable happens. Out drops a unit of length, a natural length, not chosen by humans, not based on the size of a finger or the width of a planet, but something woven out of the laws of the universe itself. That length is around 1/6 times 10 to the minus 35 meters. It is difficult to overstate how small that is. If an atom were enlarged until it was as wide as our entire solar system, the Planck length would still be far smaller than anything you could comfortably picture inside that model. It is so tiny that comparisons almost stop being helpful. Numbers at that scale slide out of intuition. They no longer feel like measurements. They feel like whispers. And yet the Planck length may not just be tiny. It may be fundamental. Now, it is important to be careful here. Physicists do not all agree that the Planck length is literally the smallest possible chunk of space, like a cosmic pixel. Science has not confirmed that. But many physicists do believe that the Planck scale marks a boundary where our current concepts of space and distance stop working in the usual way. That distinction is subtle, but important. The Planck length is not necessarily a little brick of reality sitting underneath everything else. It is better understood as a kind of frontier, a place where our familiar picture of space-time may cease to make sense. To understand why, let us imagine trying to measure something smaller and smaller. Suppose you wanted to inspect an object with incredible precision. In ordinary life, you use light. That is how sight works, and it is how microscopes work too. But the smaller the thing you want to see, the shorter the wavelength of light you need. Long wavelengths blur over tiny details. Short wavelengths can reveal them. So if you want to look at something extremely small, you need extremely short wavelengths. And extremely short wavelengths mean extremely high energy. That is the first half of the problem. The second half comes from Einstein. Energy and mass are deeply related. A large enough concentration of energy behaves gravitationally, and if enough energy is crammed into a small enough region, that region can collapse into a black hole. So now we arrive at a strange trap. To observe an extremely tiny distance, you need to focus enormous energy into an extremely tiny region. But if you focus too much energy into too small a region, gravity takes over and the region collapses. In other words, the very act of trying to probe a distance smaller than about the Planck length may destroy the space you are trying to inspect. It is one of the most beautiful paradoxes in theoretical physics. The closer you try to look, the more violently reality pushes back. It is as if the universe is saying, you may ask the question, but at some scale, the question itself stops being physically meaningful. This is why the Planck length matters so much. It is the scale at which quantum mechanics and gravity can no longer politely ignore each other. For most of physics, they can stay in separate rooms. Quantum mechanics handles atoms, particles, uncertainty, probability, and the flickering microscopic world. General relativity handles stars, planets, black holes, cosmic expansion, and the smooth geometry of spacetime. Usually that division works well enough. But at the Planck scale, both theories become equally important at once. And when we ask them to cooperate there, they do not. They produce infinities, contradictions, and broken mathematics. The old map tears. That is why the Planck length is so often described as the place where our theories reach the edge of their competence. Now, if you sit with that long enough, a new question begins to form. If space really does stop making sense below that scale, then what is space, really? We are used to treating space as a kind of background, a silent stage on which matter moves. Empty, neutral, continuous, endlessly divisible. But the Planck length hints that space may not be a passive background at all. It may have texture, structure, limits. This is a deeply strange idea, because the smoothness of space feels almost impossible to doubt. When you move your hand across a table, it does not jump from point to point, it glides. When planets orbit stars, their paths look continuous. When light travels, it seems to cross space without interruption. Everything about ordinary experience suggests continuity. But ordinary experience is not a good guide at every scale. A wooden table feels solid, but under a microscope it is mostly empty space. Water looks smooth in a glass, but at smaller scales it is made of molecules colliding and drifting. A digital photograph can look continuous from a distance, but zoom in far enough and the image resolves into pixels. Reality has tricked us before. It may be doing so again. This is where some of the most daring ideas in theoretical physics begin. If the Planck length is not just a mathematical curiosity, then maybe space itself is not continuous. Maybe what we experience as smooth extension is an emergent illusion, the large-scale appearance of something much more granular underneath. In some theories, space is built from discrete units, though not in the naive sense of tiny cubes stacked together. In loop quantum gravity, for example, areas and volumes may come in quantized amounts. In other approaches, space-time may emerge from networks of relationships, information, or causal structure rather than from a continuous geometric fabric. Different theories tell different stories, but many of them circle the same unsettling possibility: that smooth space may not be fundamental. Now, there is something calming about this idea, if you let it settle properly. Not because it is simple. It is not simple at all. But because it reminds us that reality is not obliged to match our instincts. The universe does not owe us familiarity. It can be stranger than intuition, stranger than vision, stranger even than language, and still remain lawful and beautiful. The Planck length sits at that border, where beauty becomes difficult to separate from mystery. And if you are wondering whether any of this can ever be tested, that is the right question. Physics is not just about elegant speculation. It is about what can, in principle, be observed. The challenge is that the Planck scale is so fantastically small that directly accessing it is far beyond our current technology. The energies required would dwarf anything humanity can build. Even our most powerful particle colliders are nowhere close. We are creatures of a middle scale, trying to infer the bottom layer of reality from far above it. So physicists look indirectly. They look for subtle consequences. tiny fingerprints left by whatever the deep structure of spacetime may be. Could high-energy particles behave differently over enormous cosmic distances? Could black holes reveal hints of a discrete spacetime? Could the early universe carry traces of Planck-scale physics in the cosmic background it left behind? These are difficult searches, and so far no experiment has given us a final answer. That is both frustrating and wonderful. Frustrating, because we want clarity. Wonderful, because the mystery is still alive. There is still room, at the foundation of modern physics, for a genuine unknown. And it is worth pausing there, because we live in a time when science is often presented as if it has already explained everything important, as if the grand framework is complete and only details remain. But the Planck length tells a different story. At the deepest level, we still do not know whether space is truly continuous. We still do not know what geometry becomes when quantum mechanics and gravity meet. We still do not know whether distance is fundamental, or whether it emerges from something even deeper. That is not a failure of science. That is science being honest. And honesty, in a subject this deep, is more beautiful than certainty. Now let us look at one more angle, because there is a subtle philosophical shift hidden inside all this. When we say the Planck length might be the smallest meaningful distance, we are not just shrinking the universe. We are also changing what it means to ask a question about the universe. Below everyday scales, physics already forces us to stop imagining the world in purely visual terms. Electrons are not little planets orbiting neat little suns. Particles are not always little billiard balls. Fields, probabilities, excitations, uncertainty, and relationships become more important than ordinary pictures. At the Planck scale, that trend may reach its extreme. Maybe space is not something that can be endlessly subdivided because subdivision itself is an idea borrowed from the wrong scale. Maybe asking what lies inside the Planck length is like asking what is north of the North Pole. The language suggests a direction that reality no longer supports. That possibility is humbling. So much of human thought rests on the idea that every boundary can be crossed if only we keep going. Smaller, faster, deeper, more precise. But perhaps nature contains not just practical limits, but conceptual ones. Not walls of ignorance, but boundaries of meaning. And still, even if the Planck length does mark such a boundary, it does not make the universe feel smaller. If anything, it does the opposite. Because a universe with depth beyond intuition feels larger, not in kilometers or galaxies, but in richness, in strangeness, in the number of ways reality can exceed what the mind first expects from it. The Planck length is tiny, yes, but the thought it opens is enormous. It tells us that emptiness may not be truly empty, that space may not be truly smooth, that beneath the flowing world of stars and dust and time and motion, there may be a hidden grain so fine that we only detect it through paradox. And perhaps that is one of the quiet lessons of physics. The deepest truths are often not the ones that feel grandest at first glance. They begin as a number on a page, a mismatch in an equation, a limit no one expected. And then, slowly, they widen until they change the shape of reality itself. So tonight, as you settle into the idea, imagine the fabric of the cosmos not as an endless smooth canvas, but as something that might have a final level of detail, not visible to the eye, not reachable by any ordinary instrument, but present, perhaps, in the hidden grammar of existence. A smallest meaningful length, a final whisper of distance, a place where space itself may stop being what we thought it was. And if that is true, then the universe is not just vast above us, it is also vast below us, not only in the scale of galaxies and black holes, but in the unfathomable depth of the small, in the descent from atoms to quarks to quantum fields and then onward toward a boundary where our smooth world may dissolve into something entirely new. That is where we will leave this part of the journey. In the next step, we move from the smallest meaningful distance to something just as strange, the smallest meaningful moment. Because if space may have a limit, then time may have one too. And that possibility is even harder to imagine. If this part helped you unwind, you can subscribe for more slow explorations like this one. And if you want, tell me in the comments what fascinates you more, the biggest scale in the universe, or the smallest. Both, in their own way, are endless. The smallest tick of the universe. Imagine, for a moment, that time is not flowing. Imagine that what feels like a smooth river is actually made of tiny steps. So small, so impossibly brief, that no human mind could ever notice the gaps between them. One instant, then another, then another. Not a seamless stream, but a sequence. A cosmic flicker happening so quickly that it creates the perfect illusion of continuity. It sounds unnatural at first. We are used to thinking of time as something that pours forward without interruption. Morning becomes afternoon. A thought becomes a memory. A breath becomes another breath. Time seems to glide. Even when life feels chaotic, time itself appears smooth, as if it never pauses, never stutters, never breaks into pieces. But then again, space also seems smooth. And in the last part of our journey, we found that modern physics does not fully trust that appearance. At the deepest scales, space may not be infinitely divisible. There may be a limit, a smallest meaningful length, where our familiar ideas begin to fail. The Planck length gave us a hint that the universe may have a final level of spatial detail. And if that is true for space, a very natural question follows. What about time? Could there also be a smallest possible moment? Could there be a limit beneath which the phrase, before and after, no longer makes physical sense? That is where we are going now. Gently, slowly, and without rushing past the strangeness of it. We are going to explore the Planck time, the shortest meaningful interval that appears in modern physics. We will look at where it comes from, why it matters, and what it would mean if time itself is not infinitely smooth, but built from tiny pulses too small for anything in the ordinary world to notice. And if you enjoy these quiet descents into the structure of reality, you can subscribe, leave a like, or share a thought in the comments about where you're listening from tonight. I like the idea of these questions moving softly through so many different nights. To begin, let us notice something very simple. In daily life, time feels different from space. Space feels spread out. You can point to it. You can cross it. You can measure it with rulers, roads, or shadows on a wall. Time feels more elusive. You cannot hold it in your hand. You cannot step sideways into yesterday. You cannot place 2 minutes next to each other on a table and compare their texture. Time is known through change, through motion, through memory, through decay, through the rhythm of events. A clock does not show time itself. It shows repeated motion, a swinging pendulum, a vibrating crystal, a changing electronic signal. What we call time is always tied to some physical process that marks it. That matters more than it may seem. Because in physics, just like with distance, a time interval only has meaning if some physical process could, in principle, reveal it. If there were a gap so small that no event could occur within it, or no experiment could ever distinguish it, then asking what happened during that gap might be like asking what color silence is. The words still exist, but their connection to physical reality begins to loosen. This is one reason the Planck time is so intriguing. It is not just an extremely tiny fraction of a second. It is a timescale built from the same deep constants that gave us the Planck length, the speed of light, the gravitational constant, and Planck's constant. Relativity, gravity, and quantum mechanics all meet there again. And when they do, they produce another natural unit. The Planck time is about 5.39 times 10 to the minus 44 seconds. That number is so small it almost escapes comprehension. Light, which moves fast enough to circle the Earth more than 7 times in a single second, would travel only 1 Planck length during 1 Planck time. That is not an accident. The Planck units are tied together. The smallest meaningful distance and the smallest meaningful interval are woven into the same deep scale. If the Planck length is a possible lower limit to spatial measurement, then the Planck time may be the corresponding lower limit to temporal measurement. Not necessarily because time is definitely digital in the way a computer clock is digital. That part remains unknown. But because below that scale, our best theories no longer know how to describe reality coherently. This is the key idea to hold on to. The Planck time is not just a very short duration. It may be a boundary where our usual concept of time stops working. Now, if you let that settle into your mind for a moment, it changes something quite fundamental. We usually imagine that no matter how brief a moment is, it can always be divided into smaller moments. Half a second can become a quarter of a second, then a tenth, a thousandth, a millionth, and so on. It feels natural to think that time is infinitely divisible, just like an endless decimal. But physics has learned to be suspicious of what feels natural. At ordinary scales, time does behave smoothly enough for clocks, motion, engineering, biology, and daily life. Classical physics treats time as continuous. Even in Einstein's relativity, spacetime is modeled as a smooth geometric structure. Time bends and stretches depending on speed and gravity, but it is still treated as a continuum. Then quantum mechanics enters the picture. Quantum mechanics already tells us that many things we once thought were smooth are not smooth at all. Energy comes in quanta. Electrons occupy discrete energy levels. Light can behave like packets called photons. Certain properties of the microscopic world come in jumps rather than flowing continuously. So it is not unreasonable to ask whether time, too, might have a hidden grain. That question becomes especially urgent when we approach the Planck scale. Because just as measuring smaller distances requires higher energy, measuring shorter and shorter times also leads us into deeper quantum and gravitational trouble. To examine what happens over an incredibly tiny interval, physics demands enormous precision, enormous energy, and increasingly violent conditions. Eventually, the smooth background of spacetime itself may no longer remain stable under that scrutiny. Again, the universe seems to resist our attempt to slice reality forever. There may come a point where the phrase, a smaller interval, no longer points to anything physically meaningful. If that is true, then time is not an endlessly flowing backdrop. It is not an infinite blank tape on which events are recorded. It has a fundamental grain, or at least a fundamental limit to how finely it can be resolved. Now, we should be careful once more. Physicists do not all agree that time literally ticks in separate indivisible beats. Some theories suggest that spacetime may be discrete. Others suggest that continuity may emerge from something deeper that is not quite discrete in the ordinary sense. Some approaches treat time as fundamental. Others suggest that time itself may be emergent, not basic at all. That last possibility is perhaps the strangest of all, because it means that time might not merely be made of small units. It might not exist fundamentally in the way we think it does. But before we drift that far into the deep water, let us stay close to the simple image for a moment. Suppose time does come in tiny, indivisible steps. What would that mean? At first, you might imagine a universe that jerks forward like a stop-motion film, with everything freezing and then updating at each cosmic tick. But that image is probably too crude. If there is such a thing as a smallest meaningful moment, it would be so fantastically brief that all familiar motion would remain perfectly smooth at our scale. Just as a movie looks fluid when the frames arrive quickly enough, the universe could appear continuous even if its deepest temporal structure were discrete. The analogy is not perfect, but it helps. When you watch a film, the eye does not experience individual still images. It experiences motion. The continuity is emergent. It is the result of many separate moments arriving in rapid succession. Likewise, if the universe has a smallest tick, no creature built from atoms and neurons would ever notice the individual steps directly. Our minds operate on scales vastly, unbelievably larger. A blink lasts hundreds of milliseconds. Neural signals take milliseconds too. Even the fastest electronic events in our devices are still incomparably slow compared to the Planck time. So if time does tick, it ticks far below the threshold of ordinary existence. And yet the consequences could be enormous. Because a smallest moment would mean there is a limit to how quickly change can fundamentally occur. There would be no meaningful sense in which one physical event happens in less than one Planck time. No smaller temporal resolution. No deeper slice of becoming. That does not mean the universe pauses between ticks. It means that below a certain scale, the distinction between one moment and the next may lose operational meaning. This idea touches one of the oldest philosophical questions human beings have ever asked. Is time truly something out there in the world, independent of us, flowing on whether we notice it or not? Or is time a way of organizing change, a relationship between events, something that emerges from processes rather than existing on its own? Physics does not fully settle that question, but modern theories have made it harder to think of time as a simple container. In Newton's world, time was absolute. It flowed identically everywhere, independent of matter, motion, or observation. There was one universal clock beneath the universe. Einstein changed that. Time became flexible. A fast-moving clock runs differently from a still one. A clock deep in a gravitational field runs differently from one far away. Time became part of spacetime, woven together with space, affected by motion and gravity. Then quantum theory complicated the picture even more, because in quantum mechanics, time often remains a background parameter even while everything else becomes uncertain, probabilistic, and quantized. That mismatch is one of the many reasons quantum gravity is so hard. In one theory, time is dynamic and geometric. In the other, it is often just assumed. At the Planck scale, that tension becomes impossible to ignore. Some physicists believe the difficulty is telling us that our usual notion of time is incomplete. Maybe time, like temperature or solidity, is something that emerges at larger scales from a deeper underlying reality. Think of temperature for a moment. Temperature feels like a basic property of the world. Something can be hot or cold. But if you zoom in far enough, temperature is not fundamental. What is fundamental is the motion of countless particles. Temperature emerges from their collective behavior. Perhaps time is similar. Perhaps what we call time is the large-scale appearance of something deeper: causal order, informational updates, quantum correlations, or relationships between events. In that case, the Planck time would not just be the shortest duration. It would be the scale where the familiar illusion of smooth time begins to dissolve. That is a beautiful thought, even if it is a difficult one, because it means that the river of time may be more like a pattern than a substance, more like music than water. Not a thing flowing, but a structure unfolding. Now, one place where these questions become especially intense is the early universe. If we trace cosmic history backward, the universe becomes denser, hotter, and more compressed. Galaxies merge into plasma into an even hotter sea of particles. And if we keep going back toward the beginning, there comes a stage where the conditions are so extreme that ordinary physics loses its grip. The Planck time marks that frontier. Roughly speaking, it is thought to be the earliest moment after the beginning of cosmic expansion at which our current physics can even begin to say anything coherent. Before that, or more precisely below that timescale, we do not yet possess a working theory that successfully combines quantum mechanics and gravity. That means the Planck time is not only about tiny intervals in abstract theory. It is also tied to the deepest mystery of cosmic origins. When people casually ask what happened at the very beginning, physics has to answer with unusual humility. We can describe a great deal about the early universe after the Planck era. We can talk about inflation in some models, the formation of particles, the cooling of the cosmos, the release of the cosmic microwave background, the birth of stars and galaxies. But at the Planck scale, the map fades. And that is astonishing. Not because science is weak, but because we have reached a genuine boundary of the known. It is possible that a future theory of quantum gravity will tell us what, if anything, it means to ask about before the Planck era. But it is also possible that the question, before, stops making sense there, just as smaller than the smallest meaningful distance may stop making sense spatially. If time itself has a beginning, or an emergent onset, then before time may not be a paradox. It may simply be a misuse of language. This is one of the reasons the Planck time is so profound. It is not merely a small unit. It is a limit that forces us to rethink what a moment is. And if you are feeling the strangeness of that now, that is not confusion. That is honesty. These ideas are strange. We are creatures shaped by slow clocks, sunrises, heartbeats, seasons, sleep and waking. Human time is thick and warm and lived. The Planck time belongs to a domain so far beneath experience that our intuition can only approach it indirectly, through mathematics and analogy. Still, there is something deeply human in trying, because to wonder about time is to wonder about existence itself. Every memory, every hope, every fear, every love story, every civilization, every star that was born and every star that died, all of it is bound to time. To ask whether time is continuous or granular is not just a technical question. It is a question about the texture of becoming. Does reality unfold smoothly, like a melody held in one breath? Or does it arise in tiny pulses, each one too brief to feel, but together forming everything we call history? Some approaches to quantum gravity suggest precisely that kind of pulse-like structure. In certain models, spacetime geometry may be quantized. In computational pictures of the universe, updates to the underlying structure can resemble discrete steps. In causal approaches, the order of events matters more than any smooth temporal background. Each framework tells the story differently, but many of them quietly weaken the old idea of time as an infinitely flowing continuum. And once you see that possibility, it becomes hard to unsee it. The ticking of clocks starts to feel less like time itself and more like an echo of something deeper. Seconds become conveniences. Hours become human scales. Even the smooth sweep of the cosmos begins to look like an emergent performance over a hidden foundation we cannot directly watch. Now, does that mean the universe is literally running on a cosmic frame rate? Not necessarily. That language is tempting, especially in a world full of screens, refresh rates, and digital metaphors. But nature is often subtler than our metaphors. A discrete time in fundamental physics would not have to resemble a computer clock. The underlying reality could be stranger than any familiar machine. It could involve relations, networks, probabilities, or structures for which our everyday words are only rough approximations. Still, the metaphor survives for a reason. Because it captures the central shock. That time, which feels so smooth, may have a hidden limit. A final temporal grain. A smallest meaningful tick. And there is a quiet elegance in that. If space and time both have fundamental scales, then the universe is not just vast in the large and detailed in the small. It is rhythmically bounded. It has a deep resolution. A finest level of detail beneath which the old language of here and then, distance and duration, may no longer apply in the ordinary way. The more you sit with that, the more it transforms the familiar world. A second is no longer merely a second. It is a huge ocean of possible microstructure. A simple pause between two words contains an unimaginable number of Planck intervals. A heartbeat, which feels brief to us, is a near eternity compared with the timescales where quantum gravity may begin to matter. It gives ordinary life a strange double quality. Everything is fleeting, and everything is enormous. A glance across a room is fast to us, yet built upon a depth of time so fine that human experience barely skims its surface. We live on the coarse, comfortable level of reality, where continuity works beautifully. But underneath may lie a temporal architecture so delicate and unfamiliar that our lived sense of duration is only a large-scale approximation. That does not make human time less real. It makes it layered. And perhaps that is one of the most comforting things physics can offer. Not certainty, but depth. The reassurance that even the ordinary world, the world of quiet rooms and passing nights and slow breathing, rests on mysteries far richer than it first appears. So if time is smooth, that is wondrous. And if time is made of tiny indivisible steps, that is wondrous too. Either way, the universe is more subtle than instinct suggests. As we come to the end of this part of the journey, let the idea rest gently in your mind. Somewhere beneath clocks and calendars, beneath orbits and decay, beneath memory and motion, there may be a final threshold of duration, a shortest meaningful interval, a hidden rhythm at the foundation of existence. Not a rhythm you can hear, not a pulse you can feel, but perhaps a limit written into the deep grammar of reality itself, a smallest tick of the universe. And if such a tick exists, then what we call the flow of time may be one of the greatest illusions nature has ever composed. Not a falsehood, but a beautiful appearance emerging from something finer, quieter, and far more strange. Next, we move into a clue that helps make this possibility feel less alien. Because before physicists ever wondered whether space and time might be discrete, they already discovered that nature has a habit of being surprisingly chunky. Energy itself does not come in an endless continuum. It arrives in packets. And that story is where the next part begins. If you're still here, still listening, and still letting these ideas drift slowly through the night, feel free to subscribe and tell me in the comments which feels stranger to you, a smallest distance, or a smallest moment. Nature's first clue that reality comes in pieces. Long before physicists began seriously wondering whether space itself might be grainy, or whether time might come in tiny indivisible steps, nature had already left behind a clue. A quiet clue. A clue hidden in light. At first glance, light seems like one of the smoothest things in existence. It spills across a wall in a soft gradient. It glows at dawn without sharp edges. It pours from stars across unimaginable distances and arrives here as something gentle enough to warm your skin. Light feels continuous. It feels fluid. It feels like the perfect example of something that simply flows. But that is not the whole story. Because when physicists began to look more closely, they discovered that light does something deeply strange. It does not always behave like a smooth wave spreading endlessly across space. In certain situations, it behaves like it comes in packets, little bundles, tiny chunks. And that discovery changed everything. It suggested, for the first time in a truly serious way, that the universe may not be built entirely from smooth continua. That beneath the graceful surface of reality, nature may have a preference for steps, packets, quanta, and jumps. That is where this part of our journey begins. We have already asked whether there might be a smallest distance, and whether time itself may have a smallest meaningful tick. Now we turn to a simpler, more established clue. Before asking whether space and time are pixelated, we need to understand why physicists were willing to take that possibility seriously at all. The reason is that the universe has already shown us, more than once, that smoothness can be deceptive. Energy, for example, is not always delivered continuously. In the microscopic world, it often comes in exact amounts. Matter, too, is not spread evenly through space, but organized into particles and atoms. Even angular momentum, a quantity that sounds as though it should vary smoothly, can appear only in specific allowed values. Nature, again and again, has revealed a certain grain. Not the grain of sand or wood or metal, but the deeper grain of law. The strange habit of reality to permit some values and forbid the ones in between. And once physics learned that lesson, it became much harder to assume that space and time themselves must remain infinitely smooth forever. So tonight, we are going to stay with that turning point. We will begin with the old classical picture of smooth energy, then move into the birth of quantum theory, the mystery of blackbody radiation, the strange behavior of electrons in atoms, the arrival of photons, and the deeper lesson behind all of it. Not simply that the world is weird, though it is, but that the world had already started whispering, more than a century ago, that reality may be more like a staircase than a ramp. And if you enjoy these slow wanderings through the foundations of physics, you can subscribe, leave a like, or tell me in the comments what first made you curious about the nature of reality. Sometimes one question is enough to keep the mind company for years. To understand why quantization was such a shock, we need to go back to the older picture of nature. In classical physics, the world is usually smooth. A pendulum swings through every angle between left and right. A planet passes through every point along its orbit. Water can be heated gradually. A violin string can vibrate in endlessly varied ways. Even light, in the classical view, is a wave, and waves are continuous things. Their energy can rise and fall smoothly. Their intensity can vary by any amount. That way of thinking made intuitive sense. It matched experience. If you gently turn a dimmer switch, the brightness changes smoothly. If you slowly push a cart, its speed increases smoothly. The world seemed to offer no reason to believe in hidden steps. Then a problem appeared. Actually, many problems appeared, but one of the most important began with heat and light. Physicists in the late 19th century were trying to understand how hot objects glow. A heated iron bar turns red, then orange, then white. A stove burner glows. A star shines. These are ordinary observations, but behind them lies a deep question. How exactly does a hot object emit radiation? To study this, physicists imagined an ideal object called a black body. A black body absorbs all radiation that falls on it, and when heated, it emits radiation in a pattern that depends only on its temperature. It became one of the cleanest problems in theoretical physics. At first, classical physics seemed well equipped to handle it, but when the equations were worked out, they predicted something absurd. The calculations suggested that a hot object should emit more and more energy at shorter and shorter wavelengths, rising without limit into the ultraviolet and beyond. In other words, a warm object should pour out an infinite amount of energy at high frequencies. Clearly, that does not happen. Reality refused the prediction. This mismatch became known as the ultraviolet catastrophe, and it was more than a technical annoyance. It was a sign that the smooth classical picture had hit a wall. Somewhere inside the problem, a hidden assumption was wrong. In 1900, Max Planck found a way to make the equations match observation. But the price was extraordinary. He proposed that the tiny oscillators responsible for emitting radiation in a hot object could not exchange energy continuously. They could only exchange it in specific amounts. Little chunks proportional to the frequency. Not any value. Only certain allowed values. At first, Planck treated this as a formal trick, a mathematical move to repair the problem. Even he did not fully realize how radical it was. But that move marked the birth of quantum theory. Energy, it seemed, did not always flow like water. Sometimes it arrived more like coins. Countable. Packeted. Discrete. That single idea changed the future of physics. Because once energy comes in chunks, the world is no longer as smooth as it first appeared. And that idea only became stronger when Albert Einstein took it further. In 1905, he used Planck's quantum idea to explain the photoelectric effect, another puzzle that classical wave theory could not properly handle. When light shines on certain metals, electrons can be knocked free. That much was known. But the details were strange. Very bright light of low frequency sometimes failed to eject any electrons at all, while dimmer light of higher frequency could do it immediately. Classical theory struggled with this. If light were purely a smooth wave, then increasing its intensity should eventually provide enough energy to free the electrons, regardless of color. But that is not what nature did. Einstein proposed something astonishing. He suggested that light itself comes in packets, quanta of light, later called photons. Each photon carries an amount of energy tied to its frequency. Blue light and ultraviolet light carry more energy per photon than red light. So if the frequency is too low, no individual photon has enough energy to eject an electron, no matter how bright the beam becomes. This explained the observations beautifully. And it meant that light, the thing that seems so fluid and wave-like, also has a particle-like, quantized aspect. That realization was not a minor revision. It was a fracture line running through the old worldview. Nature was not merely smooth. Nature was both wave-like and chunky, depending on how you asked the question. And once that door opened, more surprises followed. The atom, for instance, became a stage for one of the clearest examples of quantization in all of science. In the old picture, electrons orbiting an atomic nucleus should have been able to occupy any orbit they liked, just as planets can orbit at many distances. But there was a fatal problem. An accelerating electric charge should radiate energy. So an electron orbiting a nucleus should continually lose energy, spiral inward, and collapse into the atom's center. Atoms should be unstable. Matter should not endure. But atoms do endure. They are beautifully stable. So something in the old picture had to give. Niels Bohr proposed one of the first successful quantum models of the atom. In his picture, electrons were allowed to occupy only certain specific energy levels. They could not exist in between. They could jump from one level to another, emitting or absorbing light of precisely the right energy in the process. This idea explained the spectral lines of hydrogen with remarkable success. Instead of a continuous spread of possible light frequencies, hydrogen emitted only certain exact colors, sharp lines, discrete signatures. Again, the lesson was the same. Nature does not always allow a continuum of possibilities. Sometimes it permits only exact values, and everything in between is forbidden. That is such a strange idea that it is worth lingering on. Imagine climbing a hill by walking up a smooth slope. That is the classical world. Every height is available. Every intermediate position exists. Now imagine climbing by staircase instead. You can stand on one step or the next, but not in between. The smooth path has been replaced by allowed levels. That is closer to how the quantum world behaves. Electrons do not drift gradually between energies. They jump. Light is not always emitted in an endless smear. It can come in photons. Thermal radiation does not exchange energy continuously. It comes in quanta. By the early 20th century, the old dream of perfect continuity had already been wounded. Not destroyed, because continuity still works wonderfully at large scales, but wounded enough that physicists could no longer assume it was fundamental. And this is the central point for our larger question. Before anyone asked whether space or time might be made of tiny pieces, physics had already discovered that reality contains quantization elsewhere. The universe had already shown a clear taste for discreteness. That does not prove that spacetime itself is discrete, of course. We must be careful not to leap too fast. But it does make the idea feel less outrageous. If nature already quantizes energy, angular momentum, charge-like properties, and more, then perhaps the geometry of the world is not exempt. Now let us slow down and look at why quantization feels so unnatural to us. Part of the reason is that our senses evolved in a coarse-grained world. We see rivers, not molecules. We feel warmth, not the statistical motion of particles. We hear notes, not quantum transitions inside vibrating matter. Human perception smooths reality because at our scale, smoothing is usually good enough. A glass of water looks continuous, though it is made of countless molecules. A sheet of paper looks unbroken, though it is built from fibers and chemical bonds. Even a digital image on a screen appears smooth if the pixels are small enough and the distance is right. The large-scale world is full of emergent smoothness. That word, emergent, matters a great deal. Something emergent is real, but not fundamental in the deepest sense. A wave on the ocean is real, but it emerges from the collective motion of water molecules. Temperature is real, but it emerges from particle motion. Solidity is real, but it emerges from electromagnetic interactions and quantum effects inside matter. Continuity may be like that too. It may be a large-scale appearance that emerges from deeper discrete rules. In fact, one of the quiet achievements of modern physics is teaching us not to confuse appearance with foundation. Smoothness can be a surface effect. Stability can be an average. Continuity can be a useful illusion. And quantization is one of the reasons we know this. Now, beyond energy and atomic levels, quantization appears in other places too. Angular momentum in quantum systems comes in allowed units. Spin, one of the strangest properties in physics, is quantized. Certain magnetic and electrical effects depend on exact quantum values. Even the vacuum, which sounds like emptiness, behaves in ways shaped by quantum rules. The deeper physicists looked, the more the microscopic world seemed to resist smooth interpolation. Not everywhere, not in the simplest visual way, but enough to make the classical vision feel incomplete. And yet this story is not just about the world becoming chunkier. It is also about the world becoming more abstract. Because the quantum world is not made of tiny classical objects hopping around like little marbles on a staircase. Quantum states are subtler than that. An electron in an atom is not simply a little bead sitting on a neat track. It is described by a wave function, a spread of possibilities, a structured pattern that yields discrete measurement outcomes. This matters because when people hear that quantum mechanics is chunky, it is tempting to imagine a simple mechanical world made of tiny hard blocks. But that picture is too simple. Quantum discreteness is not always the discreteness of visible little pieces. Sometimes it is the discreteness of allowed outcomes, possible states, or measurable values. The grain is real, but it lives inside a world stranger than ordinary objects. That subtlety becomes important when we return to spacetime. If space and time are quantized, they may not be quantized in the way a tiled floor is tiled. The fundamental units might not be literal little cubes or identical temporal beads. The deeper structure could be relational, network-like, informational, or geometric in a new way. Quantization in physics often turns out to be more elegant and less mechanical than our first intuition suggests. Still, the precedent remains. Nature has already taught us one very important lesson. The deepest layer of reality is not obligated to be smooth just because it feels smooth to us. And perhaps that is why the birth of quantum theory remains such a profound turning point, even beyond all the technologies it eventually enabled. It changed not just the equations, but the mood of physics. Before quantum theory, many physicists believed they were polishing a nearly complete picture of the universe. After quantum theory, they realized the foundation itself was far stranger than expected. The calm surface had cracked, and beneath it lay a world of probabilities, jumps, packets, and limits. In some ways, our modern question about pixelated reality is simply the continuation of that older shock. If light can come in packets, if atoms permit only discrete energies, if angular momentum can be quantized, then maybe smooth spacetime is only the next classical assumption waiting to be revised. Not certainly, but possibly. And possibility is enough to keep science moving. There is something almost poetic in this. The first clue did not come from black holes or giant colliders or exotic cosmological events. It came from ordinary glowing objects. Heated matter. Colored lines in starlight. Light striking metal. The door into the quantum world opened through things people could observe in laboratories, through quiet puzzles in familiar phenomena. That is often how the universe reveals its depth, not by shouting, but by refusing to behave the way a smooth theory says it should. And when that refusal is taken seriously, an entire worldview can change. So as you let this part settle in, hold on to the deeper lesson beneath all the examples. Quantization is not just a technical feature of physics. It is nature's way of reminding us that continuity is sometimes an approximation, not a birthright. The world we inhabit may feel seamless, but the world underneath may be built from permissions and restrictions, from exact values and hidden steps, from discrete possibilities woven so finely together that the large-scale result looks fluid and whole. That realization makes the later question about space and time feel less like science fiction and more like the next natural extension of something physics has already learned the hard way. The universe already knows how to be grainy. It already knows how to hide steps beneath smooth appearances. It already knows how to replace a flowing slope with a staircase that only mathematics can clearly see. So perhaps, when we ask whether space and time are made of tiny pieces, we are not introducing a new kind of weirdness at all. Perhaps we are only following an older trail. A trail that began in the glow of heated matter, in the colors of hydrogen, in the sudden escape of an electron struck by light. A trail that leads from the first quantum to the deepest structure of reality. And if that trail continues, then the question becomes even more interesting. Because energy does not only come in packets. Quantum mechanics also changes what emptiness means, what motion means, and what it means for nothing to happen at all. Even the vacuum is not truly silent. Even empty space may tremble. That is where we go next. Because once nature has shown you that the world is not smoothly continuous in the ways you expected, it becomes easier to imagine that the very fabric of reality may have its own hidden texture, bubbling beneath the calm surface. If this part helped you drift a little deeper into the strange logic of the universe, you can subscribe for more, and if you want, tell me in the comments which discovery feels more surprising to you, that light comes in photons, or that electrons in atoms are only allowed to exist at certain energies. Empty space is not empty. If you were able to remove everything from a room, every chair, every table, every drifting grain of dust, every molecule of air, every trace of smoke, every photon of light, every atom, every particle, every last thing that could be taken away, what would remain? Most of us would answer in the same way. Nothing. Just emptiness. A clean absence. A silent gap where things are no longer present. It feels like one of the simplest ideas in the world. If there is something, then there is not nothing. And if all the something is removed, what remains must be empty space. A blank. A void. A stage with no actors on it. But modern physics has a habit of taking our simplest ideas and turning them inside out. Because according to quantum theory, empty space is not truly empty at all. Even a perfect vacuum, the most complete emptiness physics can imagine, is restless. It trembles. It hums. It flickers with activity too small and too brief for ordinary life to notice. Beneath the calm surface of what we call nothing, there may be a constant, invisible unrest. And that matters very deeply for our question. Because once you discover that even emptiness is active, once you realize that the vacuum itself may be full of hidden motion, it becomes much easier to imagine that the fabric of reality is not smooth and silent underneath. The idea of quantum foam, and eventually the idea of a pixelated universe, begins to feel less like fantasy and more like the next step in a pattern physics has been uncovering for more than a century. So in this part of our journey, we are going to stay with that strange revelation. We will look at what physicists mean by a vacuum, why the vacuum is not the same thing as ordinary emptiness, how virtual particles enter the story, what the uncertainty principle has to do with all of this, and why some physicists began to imagine spacetime itself as a bubbling, jittering foam at the smallest scales. And if these slow explorations into the hidden structure of reality help settle your mind at night, you can subscribe, leave a like, or tell me in the comments what idea feels stranger to you. That time may have a smallest tick, or that empty space may never really be empty. To begin, we should clear away one common misunderstanding. In daily speech, we use the word vacuum to mean a region with very little matter in it. Outer space is often casually described that way, though even outer space is not truly empty. There are atoms drifting between stars, cosmic rays moving through the darkness, photons passing by, magnetic fields, gravitational waves, and all sorts of subtle structure. But in physics, when we talk about the quantum vacuum, we mean something deeper than an empty region. We mean the lowest possible energy state of a field. That may sound abstract, but it is one of the most important shifts in modern physics. The old intuition imagines the universe as being made mainly of particles moving through empty space. The newer picture, the one used in quantum field theory, is more subtle. It says that what we call particles are excitations of underlying fields. There is an electron field, an electromagnetic field, quark fields, and more. These fields are not located only where particles happen to be. They extend throughout space. So even when no visible particles are present, the fields remain. And if the fields remain, then the vacuum is not a simple nothingness. It is the quietest state those fields can occupy, but not a state of absolute non-existence. This is a difficult idea at first, because it changes the meaning of emptiness. The vacuum is not the absence of reality. It is a state of reality, a ground level, a minimum, but not a blank. An analogy may help. Imagine a still pond late at night. No boat crossing it. No fish breaking the surface. No wind disturbing the water. From a distance it may look perfectly calm, almost like polished glass. But the water is still there. It has properties. It can ripple, carry waves, reflect light. The calm surface is not nothing. It is simply the lowest visible level of activity in that medium. The quantum vacuum is a little like that, except stranger. Because even at its lowest energy state, it cannot be perfectly still. And the reason takes us to one of the most famous principles in all of physics, the Heisenberg uncertainty principle. People often hear the uncertainty principle described as a statement about measurement, that we cannot know certain pairs of quantities, like position and momentum, with perfect precision at the same time. That is true, but it is only part of the story. The deeper message is that nature itself is not perfectly still at the quantum level. Certain quantities simply do not settle into exact values all at once. One version of this principle involves energy and time. Roughly speaking, it suggests that over very short intervals, the energy in a system can fluctuate by a small amount, as long as the fluctuation disappears quickly enough. This is not a loophole in logic. It is one of the ways quantum systems behave. And that brings us back to the vacuum. If the vacuum is the lowest energy state of a field, you might think that means its energy is exactly zero and permanently fixed. But quantum mechanics says not so fast. The fields cannot remain perfectly motionless. There is an irreducible jitter, a baseline uncertainty, a kind of permanent trembling built into the structure of the vacuum itself. These tiny fluctuations are sometimes described in terms of virtual particles. Now, that phrase has become very popular, and because of that it is also often misunderstood. Virtual particles are not exactly little permanent objects hiding invisibly in empty space like ghosts waiting to be seen. They are better understood as temporary features of quantum interactions, mathematical and physical expressions of the restless behavior of fields. But the simplified image remains useful if handled gently. According to that image, pairs of particles and antiparticles can briefly appear out of the vacuum and then disappear again. Not because the universe is breaking its own rules, but because the vacuum is not inert. The fields are active, and their activity can momentarily resemble the birth and disappearance of particle pairs. It sounds impossible the first time you hear it, something appearing from nothing. But that wording is a little misleading, because by now we have already learned that the vacuum is not truly nothing. It is more like a stage filled with silent tension. The emergence of temporary particles is not creation from absolute non-being. It is a brief reorganization of underlying fields that were there all along. This matters because once you stop imagining empty space as a blank void, the whole cosmos begins to look different. The vacuum is no longer passive. It is no longer a silent backdrop behind matter. It becomes a dynamic participant in the universe. And this is not just philosophical. There are real physical effects associated with vacuum fluctuations. One of the most famous is the Casimir effect. If you place two very closely spaced metal plates in a vacuum, quantum field theory predicts that the vacuum fluctuations between the plates will differ slightly from the fluctuations outside them. This creates a tiny measurable force pushing the plates together. It is an astonishing result, because it means the structure of the vacuum can produce real, observable effects. Even emptiness can push. Another example appears in the fine details of atomic behavior. Tiny shifts in the energy levels of electrons, such as the Lamb shift, can be explained through interactions involving the quantum vacuum. The magnetic properties of particles also reflect these subtle fluctuations with incredible precision. So when physicists say the vacuum is active, they are not indulging in poetic language. They mean it literally. Empty space, in the quantum sense, has consequences. It influences what matter does. And if the vacuum is this lively even under ordinary conditions, then what happens when gravity enters the story? That is where things begin to deepen. Because gravity, according to Einstein, is not a force acting across a stage called spacetime. It is the geometry of spacetime itself. Mass and energy tell spacetime how to curve, and spacetime tells matter how to move. In Einstein's picture, spacetime is not a passive container. It is dynamic. So now imagine combining that with quantum vacuum fluctuations. If energy fluctuates even in a vacuum, and energy affects spacetime geometry, then perhaps spacetime itself should fluctuate too. Not just matter in space, but the structure of space and time at very tiny scales. This is the seed of an extraordinary idea. At large scales, the universe looks smooth. Distances feel continuous. Time feels steady. Geometry seems calm enough for planets to orbit and galaxies to form. But at extremely small scales, perhaps around the Planck scale we discussed earlier, the hidden activity of the vacuum may become so intense that the geometry of spacetime itself can no longer remain smooth. Instead, it may quiver. It may boil. It may churn with tiny fluctuations, with temporary distortions of distance and duration, with minute bursts of curvature so violent and brief that our large-scale world never notices them directly. This picture was given one of the most memorable names in all of theoretical physics, quantum foam. The phrase was introduced by John Archibald Wheeler, who imagined spacetime at the smallest scales not as a smooth sheet but as a chaotic, frothing sea. If you could somehow zoom in far enough, beyond atoms, beyond nuclei, beyond quarks, beyond even the calm-looking geometry used in relativity, Wheeler suggested that you would not find a neat empty stage. You would find agitation. Not smooth emptiness, but bubbling structure. The analogy is beautiful. From far above, the ocean can look flat and serene. But descend closer and the apparent smoothness dissolves into waves. Closer still, into spray and turbulence and foam. The scale changes the truth. What appeared continuous at one level becomes rough and restless at another. Quantum foam says spacetime may be like that. At our scale, it looks smooth. At the deepest scale, it may be wildly unstable. In some descriptions, tiny wormholes could briefly appear and vanish. Microscopic black hole-like distortions might flicker into and out of existence. The geometry itself may fail to remain fixed, as though the stage beneath the cosmos is constantly wrinkling and unwrinkling faster than any ordinary process could detect. Now, this is where we must be careful again. Quantum foam is a theoretical picture, not an established observational fact. It is a way of imagining what the combination of quantum uncertainty and gravity might imply at the smallest scales. We do not yet have a complete theory of quantum gravity, so we cannot say with certainty exactly what spacetime does there. But the picture remains powerful because it captures something essential. The old dream of emptiness as absolute silence is gone. Modern physics does not see the vacuum as a blank void. It sees a background alive with potential, jitter, and hidden structure. And once that is true, the path toward a pixelated or discrete view of reality begins to open, because there are now two broad possibilities. One possibility is that spacetime remains fundamentally continuous, but becomes violently fluctuating at tiny scales, smooth in principle, but practically turbulent. The other possibility is that this apparent turbulence is a clue that continuity itself is the wrong starting point, that spacetime only looks smooth from far away, while underneath it is built from some discrete, relational, or quantized structure that merely appears continuous at larger scales. Quantum foam does not settle that question, but it pushes us toward it. It says, whatever spacetime is, it may not be the calm continuum our intuition imagined. There is something quietly profound in that, because emptiness is one of those ideas human beings have always used to comfort ourselves with simplicity. If the world becomes too full, too complicated, too heavy, we imagine there is at least such a thing as nothing, a place of total absence, a clean conceptual zero. But physics has slowly taken even that away. There is no simple nothing waiting underneath reality. There is no silent floor beneath the universe where existence ends and blankness begins. Instead, there is structure, field, uncertainty, possibility, restlessness. Even the void has texture. And if you let that sink in, it changes the emotional shape of the cosmos. The universe becomes less like a machine moving through emptiness and more like a living web of layered activity, with visible matter floating on top of deeper invisible processes. A star is no longer just a bright object in an empty dark. It is an island of hot matter suspended in a sea of fields, fluctuations, geometry, and hidden law. A vacuum is no longer a blank region. It is a subtle state, tense with potential. Silence itself is no longer truly silent. Now, why does all this matter for our larger story about pixelated reality? Because before you can accept that space and time might have a smallest scale, you have to first loosen your attachment to the old image of empty space as a featureless stage. Quantum vacuum theory helps do exactly that. It teaches us that the stage is active. It has properties. It fluctuates. It may even generate observable effects from what appears, at first glance, to be nothing at all. Once that lesson is learned, the next step becomes easier. If the vacuum can have hidden structure, then perhaps spacetime can too. If emptiness can fluctuate, then perhaps geometry can fluctuate. And if geometry becomes unstable at tiny scales, then perhaps smooth spacetime is not fundamental, but emergent. This is why the path from quantum theory to quantum gravity feels so natural in hindsight. The universe kept offering the same lesson in different forms. Light is not only a wave. Energy is not always continuous. Atoms do not permit every state. Emptiness is not empty. Again and again, reality refused the simplest classical picture. Again and again, what looked smooth from afar dissolved into something stranger up close. And that pattern should feel familiar by now. Water looks continuous until you think in molecules. A digital image looks smooth until you notice pixels. Time feels flowing until you ask whether there is a smallest meaningful interval. Space feels continuous until you confront the Planck scale. The vacuum feels empty until quantum theory shows you the motion underneath. Everywhere, the same quiet warning returns. Do not mistake appearance for foundation. Now, some physicists have tried to test whether spacetime itself really has this foamy character. One idea is that if light travels across billions of light years through a fundamentally jittery spacetime, perhaps the foaminess would leave tiny distortions in the light's arrival, blur the images of distant sources, or slightly alter the behavior of extremely energetic photons. So far, the universe has been stubbornly smooth in the observations we can make. If foam exists, it may be more subtle than some early pictures suggested, or its effects may hide in ways we have not yet learned to isolate. That uncertainty is important. It reminds us not to turn elegant theory into premature certainty. Still, whether quantum foam in Wheeler's image turns out to be exactly correct or not, the deeper lesson remains alive. The vacuum is not nothing, and that is already enough to change how we think. It means that reality has depth even where it appears absent. It means the universe is structured all the way down, even in places where the senses report blankness. It means there may be no true empty stage behind the cosmic drama, only deeper layers of the drama itself. And perhaps that is one of the most calming truths science can offer. That what looks empty is not barren. That silence can contain hidden motion. That the dark between stars is not dead. That the void itself may be rich with unseen life of a kind, not biological life, but physical unrest, subtle and lawful and constant. As we come to the end of this part, let the idea rest gently. Imagine the emptiest region you can picture. A vast black distance between galaxies. No planet, no star, no dust cloud, no visible thing, only darkness. And now imagine that even there, the fields remain. Even there, the vacuum fluctuates. Even there, at scales too small for sight or touch, existence refuses perfect stillness. The universe does not easily allow absolute nothing. It prefers a quieter kind of something. A trembling underneath silence. A flicker underneath emptiness. A foam underneath the smooth. And if that is true, then the next question becomes unavoidable. If the vacuum is alive with hidden fluctuation, what kinds of deeper theories could explain the structure beneath spacetime itself? What would it mean to stop treating space as smooth altogether, and instead imagine that it is woven from more fundamental pieces? That is where the next part of our journey leads. If this section helped you settle in a little more deeply, you can subscribe for more slow explorations like this, and if you want, tell me in the comments which feels more unsettling in a calm way, that empty space is active, or that spacetime itself may not be fundamental at all. If space has atoms, at some point, after following all of these clues far enough, a strange thought begins to feel almost reasonable. If energy comes in packets, if atomic states come in allowed levels, if the vacuum itself is never truly still, and if spacetime seems to reach a breaking point near the Planck scale, then maybe the smoothness of space is not fundamental after all. Maybe space, too, comes in pieces. Not pieces we can see. Not little cubes floating inside a larger emptiness. Not bricks stacked in some cosmic warehouse. But something more subtle, more abstract, more beautiful, in a severe and quiet way. What if the very thing we call space is woven out of tiny indivisible units, so small that no ordinary measurement could ever resolve them directly? What if area and volume are not endlessly divisible, but come in minimum amounts, the way energy does in quantum physics? What if the smooth room around you, the distance between stars, the emptiness between galaxies, all of it is only the large-scale appearance of a finer hidden structure? This is one of the boldest ideas in modern theoretical physics. And in this part of our journey, we are going to stay with one of the most important attempts to make that idea real, loop quantum gravity. You do not need to memorize equations to feel the power of it. What matters is the central intuition. Einstein taught us that gravity is not a force pulling through space like an invisible rope. Gravity is geometry. Matter curves space-time, and that curvature guides motion. Space and time are not the background. They are part of the story. So if we want to bring gravity into the quantum world, we cannot just quantize particles moving through space. We may have to quantize space itself. That is the radical move. Not quantum things in space, but quantum space. And if these calm descents into the deeper structure of reality help you unwind at night, you can subscribe, leave a like, or tell me in the comments what feels stranger to you. The idea that empty space fluctuates, or the idea that space might be made of tiny units too small for the universe to let us see directly. To begin, let us slow down and remember what Einstein changed. Before relativity, it was natural to think of space as a fixed stage. Matter moved across it. Forces acted within it. Time ticked forward independently. The stage remained in place while the objects upon it performed their motions. Einstein took that stage away. In general relativity, spacetime itself becomes dynamic. Massive objects do not merely sit inside space. They shape it. A star bends the geometry around it. A planet follows the curves of that geometry. A black hole is not simply an object in space. It is a region where the geometry becomes so extreme that the ordinary structure of spacetime is radically altered. This was one of the most profound shifts in the history of science. Space was no longer passive. It could stretch, curve, ripple, expand. And yet, for all its brilliance, Einstein's theory still treats spacetime as continuous, smooth, infinitely divisible, at least in its mathematical form. No smallest patch of area. No smallest chunk of volume. Just geometry all the way down. That works astonishingly well on large scales. But now we know what happens when we push too far toward the small. The Planck scale appears. Quantum uncertainty becomes impossible to ignore. Gravity and quantum mechanics collide. Our equations stop cooperating. The smooth picture begins to fail. So a natural question emerges. If gravity is geometry, and everything else in the microscopic world seems to be quantized in some way, why should geometry alone remain continuous? Why should space be exempt from the quantum revolution? Loop quantum gravity is one of the deepest attempts to answer that question. Its central claim is both simple and dizzying. Space is not continuous at the smallest scale. It has a discrete structure. Area and volume come in tiny indivisible units. The smooth spacetime of Einstein is not fundamental. It emerges when you zoom out, the way a fabric looks smooth from a distance even though it is woven from threads. That image of weaving is a good one. Because in loop quantum gravity, space is often described not as a blank container, but as a network, a web, a structure made of connections. The mathematical details are difficult, but the broad picture can be felt without them. Imagine that beneath the world of smooth distances, there is a hidden network of nodes and links. The links carry quantum information about area. The nodes carry quantum information about volume. This network is not in space. It is space, or at least the deep quantum scaffolding from which the familiar notion of space emerges. That distinction matters a great deal. We are used to imagining little things existing inside a larger arena. Pebbles inside a box. Dust in sunlight. Planets in space. But if loop quantum gravity is even partly right, the fundamental entities are not sitting inside space the way furniture sits inside a room. They are what give rise to the room itself. This is very hard for the mind to picture, because our imagination is built from ordinary objects placed in ordinary space. But physics often goes beyond what the imagination can easily hold. And sometimes the best we can do is approach the truth with metaphors. One useful metaphor is woven cloth. From far away, cloth looks continuous, smooth, soft and unbroken. But up close, that continuity dissolves into interlaced threads. The smooth surface was real in one sense, but not fundamental. It was an emergent appearance created by finer underlying structure. Loop quantum gravity suggests that spacetime may be like that. The smooth geometry we move through every day may be the large-scale appearance of an underlying quantum weave. Now, why is it called loop quantum gravity? The name comes from the mathematical variables used in one formulation of the theory, where loops and networks naturally arise in describing the quantum states of geometry. Over time, these ideas led to the picture of spin networks, which are one of the most important visual and conceptual tools in the theory. A spin network is a graph made of edges and nodes. The edges are labeled by quantum numbers, and these labels correspond to discrete amounts of area. The nodes, where several edges meet, correspond to chunks of volume. Again, this is not a graph drawn inside a larger space. It is meant to be a representation of the quantum state of space itself. That is one of the most startling ideas in all of modern physics. The space around you may have a finite quantum grain, not because it is made of little visible particles, but because its geometry is built from relationships that only permit certain discrete values. This means that just as an electron in an atom cannot have just any energy, a region of space may not have just any area or volume. There may be minimum units, minimum chunks. Not because nature likes awkward limits, but because that is how quantization works. It does not always create tiny heart-building blocks. Sometimes it creates allowed values. That subtlety is important. When people hear the phrase atoms of space, it is tempting to imagine miniature marbles of emptiness packed together like oranges in a crate. But that image is much too classical. Loop quantum gravity is not saying that space is made of little lumps sitting in a bigger void. It is saying that the measurable properties of geometry itself, things like area and volume, may come in discrete quantum amounts. In other words, the graininess belongs not to matter in space, but to space as such. And once you understand that, the theory begins to feel less like science fiction and more like a natural extension of the quantum lesson we have already seen many times. The old classical world believed in continuity. Quantum theory repeatedly found discreteness hiding underneath. So when relativity gives us a smooth geometric spacetime, it is not unreasonable to wonder whether that smoothness, too, may be an emergent approximation. Loop quantum gravity says yes. Now let us pause and ask what this would mean for motion. In ordinary life, movement feels continuous. A hand reaches across a table. A planet circles a star. A beam of light crosses a room. We experience position as something that can vary without interruption. If space has a discrete quantum structure at the deepest level, does that mean motion is really a kind of hopping from one chunk to another? The answer is not simple, and the honest version is that the theory does not reduce neatly to a cartoon of jumping dots. At large scales, continuous motion still emerges, just as smooth curves emerge in many systems built from tiny parts. But at the deepest level, the structure underlying that motion may not be continuous in the old classical sense. This is similar to the way a digital image can display a smooth diagonal line even though it is made of pixels. The smoothness is real at the scale we experience it, but it emerges from a discrete base. Loop quantum gravity invites us to imagine that physical space itself may have a similar hidden resolution. Not necessarily in a square grid, not in the style of a simple computer screen. The geometry could be much more flexible and subtle than that, but still, a resolution, a smallest meaningful granularity. And if that is true, the consequences are immense. One of the most interesting consequences appears in black holes. In classical general relativity, if enough mass collapses under gravity, the mathematics points toward a singularity. Density rises without limit. Curvature becomes infinite. The equations no longer produce physically meaningful answers. Physicists have always treated singularities with suspicion. They are not usually interpreted as real features of nature so much as signs that the theory has reached the edge of its validity. Loop quantum gravity offers one possible way out. If space itself has a minimum quantum structure, then perhaps it cannot be crushed into an infinitely small point. There is a lower limit to volume, a smallest meaningful geometric chunk. In that case, gravitational collapse may not proceed forever toward infinity. Instead, it may hit a quantum limit. Some researchers working in loop quantum gravity have proposed that the center of a black hole might not be a singularity at all, but a region of extremely dense quantum geometry, sometimes described in related contexts with ideas like a Planck star. The collapse would be halted by quantum gravitational effects before infinite density is reached. This is a deeply attractive possibility. Not because it is proven. It is not. But because it suggests that a quantum structure of space might naturally remove the infinities that plague classical gravity. And what is true for black holes may also matter for the beginning of the universe. In classical cosmology, tracing the expansion of the universe backward leads to another singularity, the Big Bang understood as an infinite compression of everything into an infinitely dense point. But again, if space has a minimum quantum structure, perhaps that infinite beginning is not the literal truth. Perhaps the universe never reaches zero volume. Perhaps there is a bounce, or some other quantum gravitational transition, where the classical picture gives way to something new. This is one of the reasons loop quantum gravity has generated such enduring interest. It does not just propose a strange microscopic structure. It also offers the hope of curing some of the most troubling infinities in modern physics. That hope matters. Again and again in science, infinities appearing in physical theories are warning signs. They often mean the theory is being pushed beyond where it can be trusted. A quantized geometry offers one possible way to say, no, nature does not actually permit the continuum to continue forever. There is a lower floor. A final grain, a quantum limit built into the fabric itself. Now, if you are listening carefully, you may notice something beautiful here. For centuries, human beings imagined the deepest truths of the universe as ever more refined versions of smoothness, a purer geometry, a cleaner continuum, an infinite divisibility. But quantum theory keeps leading us in a different direction, not toward a smoother world, but toward a more structured one where continuity is often only a large-scale appearance. Loop quantum gravity fits that pattern perfectly. It says the smoothness of space is real enough for planets, galaxies, and human life. But deep down, beneath the scale where ordinary intuition still helps, geometry may have a hidden atomism. Not atomism in the old materialist sense of tiny hard particles bumping together, but atomism of a more modern and subtle kind, quantized relations, discrete spectra, allowed chunks of area and volume. That may sound cold or abstract at first, but there is something almost poetic in it too. The emptiness around us, which feels so open and seamless, may actually be woven with unimaginable fineness. The silence between stars may rest on a structure more delicate than anything the senses can detect. The room around your body may be supported, in the deepest sense, by a quantum network so small and so strange that ordinary language can only circle it. And yet from that hidden structure come all the smooth things we know. The arc of a falling leaf, the horizon at dusk, the slow spin of galaxies, the path of light across the night. A woven universe can still look continuous. In fact, that is exactly what weaving does. Now, loop quantum gravity is not the final answer to the problem of quantum gravity. It has real challenges, and those challenges matter. One of the biggest is showing clearly and convincingly how the familiar smooth spacetime of general relativity emerges from the underlying quantum structure in the right limit. That may sound like a technical issue, but it is actually central. A theory of quantum space cannot merely be elegant in the small. It must also reproduce the world we already know in the large. There are also challenges in making contact with experiment. The Planck scale is so tiny that direct tests are extraordinarily difficult. A theory can be mathematically compelling, philosophically rich, and still remain unconfirmed by observation for a very long time. This is where humility becomes essential. Loop quantum gravity is not established fact. It is one of the leading ideas, one of the most serious attempts to quantize geometry, but it remains part of an unfinished scientific story. Still, unfinished does not mean unimportant. Some of the greatest ideas in science spend long periods in an in-between state, not yet fully confirmed, but too fertile and too coherent to ignore. They shape the questions. They change the vocabulary. They alter what future answers will even look like. Loop quantum gravity has already done that. It has made it possible to speak seriously, mathematically, and rigorously about the quantum structure of space itself. It has taken the old philosophical phrase atoms of space and given it modern content. It has shown that the idea of discrete geometry is not merely a fantasy, but a framework that can be pursued with discipline and depth. And perhaps that is enough, at least for now, to justify wonder. Because wonder does not always need closure. Sometimes it is enough to realize that the space you have always taken for granted may not be the smooth emptiness it appears to be. That geometry itself may be quantized. That the distance between 2 points may not remain meaningful all the way down. That beneath the seamless surface of reality there may lie a hidden weave of area and volume, nodes and links, a structure so fine that even the emptiest room is full of silent architecture. As we come toward the end of this part, let the image settle gently. Not a universe built from visible blocks. Not a crude digital grid. But a cosmos whose smoothness may be emergent, whose geometry may be quantized, whose space may have atoms in the deepest and strangest sense of the word. The stars above you would still shine. Gravity would still guide planets. Light would still travel. But underneath it all, there may be a quantum weave, a fabric whose threads are too fine for sight, too fundamental to sit inside anything larger, and too important to ignore if we want to understand what reality is made of. And if space can be woven this way, then another question naturally follows. If geometry emerges from a network, if the fabric is not fundamental but constructed, then what else might reality emerge from? Could the universe be less like a material object and more like a process? Less like a static structure and more like a computation unfolding step by step? That is where the next part of our journey leads. If this helped you drift a little deeper tonight, you can subscribe for more slow explorations like this, and if you want, tell me in the comments which image stays with you more, space as a smooth fabric, or space as a hidden quantum weave. If the universe is a process, not a place, there is a moment in every deep scientific question when the mind quietly changes direction. At first, we ask what things are made of. We ask about particles, matter, atoms, stars, fields. We look for ingredients, building blocks, the pieces from which the visible world is assembled. But eventually, another possibility begins to appear. What if reality is not fundamentally made of things at all? What if, at the deepest level, the universe is made of events, updates, relationships, transformations? What if the world is not best understood as a collection of objects sitting in space, but as a process unfolding step by step? Not a finished structure, but an ongoing computation. Not just a place where things happen, but something that is happening. That idea may sound modern, almost digital, but its roots are older than computers. It grows from a simple and unsettling observation. Again and again, physics has forced us to let go of the background we once trusted most. Matter became less solid than it seemed. Space became dynamic in relativity. The vacuum turned out not to be empty. Even geometry itself, in some theories, may be quantized. So perhaps the next layer down is not a smoother substance hiding beneath everything else. Perhaps the next layer down is rule, pattern, update. A universe that does not merely contain change, but is change all the way down. That is the spirit behind one of the more unusual and provocative ideas in modern theoretical physics, the thought that reality may be fundamentally computational. Not necessarily in the crude sense that the universe is literally a laptop running somewhere else. That metaphor is too thin, too mechanical, too easy. The deeper idea is subtler. It is that simple underlying rules, applied again and again, might generate the complex spacetime world we experience, just as simple rules in mathematics can generate patterns far richer than anyone would guess from the rules alone. And if these quiet descents into reality's hidden structure help you settle in at night, you can subscribe, leave a like, or tell me in the comments which feels stranger to you: space being woven from quantum geometry, or the idea that the universe may be better described as an unfolding process than as a static place. To begin, let us notice something familiar. In ordinary life, we often describe the world as if it were made of objects first and action second. A stone exists, then it falls. A tree exists, then it grows. A planet exists, then it moves. The noun comes first. The verb comes later. That feels natural because our minds are built to track stable things. We evolved to notice bodies, edges, motion, danger, shelter, food. We live in a world where object thinking is useful. But physics has slowly complicated that picture. Light sometimes behaves like a particle, but also like a wave. Particles themselves begin to look like excitations of deeper fields. Space is no longer a passive container in general relativity. In quantum mechanics, the outcome of an interaction can matter more than the idea of a little object carrying fixed classical properties through time. The closer we look, the more the universe begins to resemble a web of relations and events rather than a pile of self-contained objects. So the idea of process is not coming from nowhere. It is emerging from a long history of reality refusing to sit still as a collection of simple things. Now imagine pushing that trend further. Imagine that beneath particles, beneath fields, beneath even smooth spacetime, there is something more abstract but perhaps more fundamental, a set of relationships that changes according to rules. At each step, the structure updates. Connections form, dissolve, rearrange. And out of that repeated unfolding, what we call space, time, matter, and causality emerge. This is one way to think about the computational universe idea associated with projects like the Wolfram Physics Project. The details can become technical very quickly, but the core picture can be approached gently. Suppose you begin not with particles in space, but with a network, a collection of points related to one another. Then suppose there is a simple rule that says when a certain pattern of connections appears, it should be replaced by another pattern. The rule is applied, then applied again, and again. Over many updates, the network grows and changes. At first that sounds almost too simple to matter. But simple rules can create astonishing complexity. This is one of the quiet revelations of computational thinking. You do not always need elaborate instructions to produce elaborate structures. A tiny mathematical rule, repeated many times, can generate branching forms, unexpected symmetries, chaotic patterns, and behavior so rich that it becomes difficult to predict without just letting the process run. In other words, simplicity at the level of rule does not mean simplicity at the level of result. And that matters for the universe. Because one of the deepest hopes in theoretical physics has always been that the bewildering complexity of the cosmos may emerge from something simpler underneath, a small set of principles, a hidden order. Not a universe held together by endless exceptions, but one whose richness unfolds from deep and elegant foundations. The computational view offers one possible version of that dream. Instead of imagining spacetime as fundamental, it imagines a more primitive underlying structure whose repeated updates generate something that looks, at large scales, like spacetime. Space is not pre-given. It is the pattern of relations. Time is not an external river flowing over the system. It is the ongoing act of update itself, the sequence through which the structure transforms. That is a radical shift. It means that space may be emergent from connectivity, and time may be emergent from transformation. The universe, in that picture, is not sitting inside time while it evolves. Its evolution is what time is. This is difficult to picture at first, but perhaps an analogy can help. Imagine reading a story one sentence at a time. The world of the story seems to exist, but it only unfolds as the sentences arrive. The sequence is not happening inside the story. It is generating the story. In a loose sense, the process of telling is what gives rise to the world being told. Now imagine something far more abstract and precise than language, a rule-governed transformation of structure rather than words on a page, and you begin to approach the intuition. The universe may not be a finished object sitting there in full all at once. It may be an active unfolding, a continual becoming. Now, one reason this idea attracts attention is that it offers a new way to think about why the universe looks lawful. If reality grows from the repeated application of simple underlying rules, then lawfulness is not imposed from outside. It is built in from the beginning. Regularity emerges because the updates themselves are regular. And surprisingly, some features of known physics can begin to appear in these kinds of frameworks. Researchers working in computational approaches have argued that under certain conditions, structures resembling relativistic behavior, causal order, and even quantum-like branching can emerge from underlying rewriting systems. The claim is not that every detail is solved, far from it, but that perhaps spacetime geometry, particle-like behavior, and quantum phenomena might all be the large-scale shadows of a deeper combinatorial process. This is one of the reasons the idea feels so provocative. It does not merely tweak the existing picture. It asks whether the picture itself should be turned inside out. Instead of matter moving through space and time, perhaps space and time are themselves products of an ongoing generative system. Instead of asking what the universe is made of, perhaps we should ask what rules it follows in becoming what it is. Now, if you are feeling a little resistance to this, that is perfectly natural. Because process is harder to hold in the mind than substance. We like to imagine stable things. Processes feel slippery. They are harder to point at, harder to draw, harder to picture resting somewhere. And yet process is everywhere in lived experience. A flame is not really a thing in the same way a stone is a thing. It is a continual reaction, a pattern sustained by change. A whirlpool is not a static object. It is flowing structure. A melody is not a material item. It is an ordered sequence. A storm, a heartbeat, a conversation, a thought, all of these are better understood as processes than as inert things. Perhaps reality itself belongs more to that family than we once thought. Not a thing. A pattern that persists through transformation. And this possibility becomes even more intriguing when we consider time. We have already spoken about the Planck time and the possibility that there may be a smallest meaningful interval. In a computational or process-based view, that idea feels less alien. If the universe unfolds through updates, then time naturally acquires a step-like character at some deep level, not necessarily in the simple style of a digital clock, but in the sense that becoming may be structured by transitions rather than by a smooth metaphysical flow. Again, one must be careful. The metaphor of a computer can mislead as much as it helps. Real physics is not obliged to resemble our machines. Our machines are tiny local inventions built inside the universe. They are not privileged models of ultimate reality. Still, the metaphor survives because it captures something useful. Rules can generate worlds. Simple updates can generate complexity. And what looks continuous from far away can emerge from discrete operations underneath. That lesson fits surprisingly well with everything we have seen so far. The Planck scale suggests a limit to smooth resolution. Quantum theory already teaches us that many quantities come in discrete values. The vacuum is active, not silent. Loop quantum gravity suggests a quantized geometry. A process-based picture takes the next step and asks whether the deep structure of reality might be less like a fabric and more like an unfolding network. And if that is true, then something profound happens to the idea of place. Place becomes secondary. What matters first is relation. This point is easy to miss, but it may be one of the deepest in the entire story. We usually imagine that objects are first located somewhere, and then enter into relations. This cup is here. That star is there. Then we ask how far apart they are, how they interact, whether one influences the other. But in many modern approaches, relation may come first. Connectivity, causality, adjacency, interaction, these may be more fundamental than the smooth geometric space in which we later embed them conceptually. In other words, what is near to what may matter before what distance even is. That is a remarkable inversion. It suggests that geometry may arise from structure, not the other way around. That the map of reality is not drawn on a prior space, but grows from deeper patterns of connection. And once you entertain that, the familiar world begins to look a little different. A room is no longer just an empty volume with objects in it. It is a stable, large-scale appearance of underlying relations. A galaxy is not merely a cluster floating in an infinite container. It is part of an evolving structure whose geometry may itself be emergent. Even the quiet interval between two thoughts may rest on a deeper order of updates and correlations, hidden far below any conscious awareness. Now, there is another reason process-based views are compelling. They may help explain why the universe can be both lawful and creative at the same time. A rigid clockwork universe of classical imagination can feel overly fixed. Everything seems pre-written, every motion merely the consequence of earlier motion. Quantum mechanics disrupted that certainty with probability, branching, and unpredictability. A computational or rule-based universe can potentially hold both sides together. The rules are definite, yet their unfolding can generate immense complexity, surprise, and even irreducibility, behavior that cannot be shortcut but must actually happen step by step. That idea, sometimes called computational irreducibility in related contexts, is quietly powerful. It means some systems cannot be understood by finding a closed-form shortcut. To know what they do, you have to let them run. If something like that applies to reality at a deep level, then the universe is not merely a static theorem waiting to be read all at once. It is an unfolding whose future structure genuinely depends on the continuation of the process. There is something almost alive in that. Not alive in the biological sense, of course, but alive in the sense of active, generative, not fully reducible to a frozen blueprint. This does not mean the computational view is proven. It is not. Like all frontier ideas in quantum gravity and foundational physics, it remains unfinished, debated, incomplete. Many physicists remain skeptical. Others find it fertile and worth exploring. That is exactly where deep science often lives for long stretches of time, between intuition and confirmation, between possibility and evidence. And that is all right. Because the value of such a theory is not only whether it is already complete, it is also whether it helps us ask a better question. And here, it does. It asks whether reality is fundamentally static or generative, whether space and time are given in advance or arise from deeper structure, whether the universe is best thought of as a place containing events or as an event-like unfolding that gives rise to place. Those are not small refinements. They are shifts in worldview. And perhaps one of the most beautiful things about them is that they return us, strangely, to a more ancient intuition. Many philosophies and spiritual traditions have long treated reality not as fixed substance but as flow, process, becoming. Physics does not simply repeat those traditions, and it must not be forced into them. But it is interesting that after centuries of object thinking, science too has begun to see that change, relation, and unfolding may belong much closer to the base of reality than we once assumed. The universe, then, may not be a grand sculpture standing still in the dark. It may be more like a quiet act of continuous making, a generative order, a deep ongoing computation of relations, a cosmos not merely existing, but happening. As we come toward the end of this part, let that possibility rest softly in your mind. The stars still shine. Galaxies still turn. Your room is still your room. Nothing in daily life needs to feel less real. But underneath the calm appearance of stable objects and familiar places, there may be a deeper layer where the universe is not fundamentally made of things resting somewhere. It may be made of transformations, updates, relations, structures unfolding one step into the next. And if that is true, then the next question becomes almost unavoidable. If reality arises from deep structure, whether woven geometry or generative process, could there still be observable limits to what the universe can store, measure, or contain? Could the cosmos itself have something like a resolution limit, not only in space and time, but in information? That is where the next part of our journey goes. If this part helped you sink a little deeper into the mystery, you can subscribe for more slow explorations like this, and if you want, tell me in the comments which image stays with you more, the universe as a place, or the universe as a process. If reality has a resolution limit, if space and time are not perfectly smooth, then a quiet but enormous question begins to rise out of the darkness. Would we be able to tell? Not by staring at a wall or watching clouds move overhead. Not by looking at a tree, or the moon, or the slow passing of an ordinary afternoon. If reality has a hidden grain, it must be so fine that everyday life glides right over it without noticing. The world feels continuous because, at our scale, it behaves as though it is. But what if the smoothness we experience is only a large-scale illusion? What if, at some extreme depth of reality, there is a final limit to detail? A deepest level of resolution. A point beyond which space cannot be subdivided, time cannot be sliced, and perhaps information itself cannot be packed any more densely. That idea is where our journey turns now. Because once you begin to suspect that the universe may have a smallest meaningful length, a smallest meaningful moment, a quantum weave of geometry, or even an underlying process from which spacetime emerges, another question naturally follows. If the world has a hidden resolution, then surely that resolution must have consequences. It cannot just sit there forever, doing nothing. Somewhere, somehow, it should matter. So in this part, we are going to move from theory toward implication. Not proof, not certainty, but implication. We will explore what kinds of signs a pixel-like reality might leave behind. We will look at the idea that the universe may contain a limit to information density, why some physicists think reality may be more about information than substance, and how principles like the holographic principle and the Bekenstein bound opened the door to one of the strangest thoughts in modern science, that the deepest structure of the universe may not be written in volume at all, but on surfaces. And if these slow descents into the quiet edges of physics help you relax at night, you can subscribe, leave a like, or tell me in the comments what feels more mysterious to you, the idea that spacetime has a smallest scale, or the idea that the universe might have a built-in information limit. To begin, let us think about resolution in a simple way. Take a digital photograph on a screen. From a normal viewing distance, it looks smooth. A face appears continuous. A sunset blends softly from gold to blue. The edges seem fluid, natural, unbroken. But if you zoom in far enough, the image changes character. The smoothness dissolves. You begin to see pixels, tiny colored units arranged in a grid. At that point, asking for more detail becomes meaningless. The image has reached its underlying resolution. You cannot uncover a sharper version by zooming further into what is already there. You can only magnify the grain. Now, the universe is not literally a computer image. That comparison is only a metaphor, and like all metaphors, it has limits. But it helps us approach the deeper idea. A world with a fundamental smallest scale may behave, in some ways, like a world with finite resolution. Smooth from a distance, granular at the base. And if that is true, then one of the first things we should ask is this: how much information can fit into a region of space? At first, that sounds like a modern question, almost technological. We think of information in hard drives, memory chips, files, and signals. But in physics, information has become something much broader and more fundamental. It is tied to the number of distinguishable states a system can have. It is tied to entropy, to structure, to possibility, to what can, in principle, be known, stored, or encoded in a physical system. This shift toward information is one of the great conceptual changes in modern physics. The older picture of reality was mostly about matter and energy, solid things, motion, force, geometry. The newer picture still cares about those things, of course, but it increasingly asks a different kind of question beneath them. How much information does physical reality contain? How is that information arranged? And are there limits? Once physicists began asking those questions, something startling appeared. It turned out that gravity seems to impose deep constraints on information. One of the earliest and most important hints came from thinking about black holes. Now, black holes have a strange way of pulling almost every major question in physics toward themselves. They are not just heavy objects. They are pressure points where our theories become uncomfortable. They force relativity, quantum mechanics, thermodynamics, and information theory into the same room. And one of the most surprising discoveries about black holes is that they seem to have entropy. Entropy, in physics, is often associated with disorder, but more deeply it is connected to the number of microscopic ways a system can be arranged while still looking the same from the outside. It is also deeply linked to information. A system with higher entropy can, in a sense, encode more microscopic possibilities. In the 1970s, Jacob Bekenstein and Stephen Hawking helped reveal something profoundly strange. A black hole's entropy does not scale with its volume. It scales with the area of its event horizon. That is not what ordinary intuition would suggest. If you fill a box with gas, the amount of stuff inside seems naturally related to the volume of the box. More room, more particles, more possible states. Volume feels like the place where content belongs. But black holes do something different. Their entropy, the measure tied to their information content, grows with the surface area surrounding them, not the volume inside. That may sound like a narrow technical detail, but it is one of the most disturbing and beautiful clues in all of theoretical physics. Because it suggests that the fundamental information describing a region of space may be tied not to the volume, but to the boundary. That is such a radical idea that it took decades to fully appreciate how strange it really is. Imagine a library whose total content is determined not by how big the inside is, but by the area of its walls. Imagine a room whose deepest possible informational description does not live in the room, but on its surface. This is the kind of conceptual reversal black hole physics began to hint at. And from that reversal emerged one of the most famous ideas in fundamental physics, the holographic principle. The holographic principle is subtle, but its basic intuition can be approached gently. A hologram is a surface that can encode a three-dimensional image. The full appearance of depth emerges from information stored on a lower dimensional boundary. In a somewhat analogous way, the holographic principle suggests that the physics inside a region of space may be fully describable by information encoded on its boundary. The universe, or at least some regions of it, may behave as though the deepest description lives on a lower dimensional surface, while the volume we experience emerges from that. This does not mean the world is fake. It does not mean your room is an illusion in the cheap sense, or that stars are only projections in a trivial sense. The idea is much more profound and much harder to picture. It means that the bookkeeping of reality, the deepest accounting of possible states, may not work the way everyday intuition expects. Volume may be less fundamental than boundary. The inside may emerge from the edge. And if that is true, then a region of space does not have infinite informational capacity. It has a limit. That limit is one of the reasons the universe begins to look less like a perfectly smooth continuum and more like something with a deepest resolution. Because a truly continuous region, in the naive classical sense, seems capable of containing infinite detail, you could specify smaller and smaller variations forever. But once gravity, quantum theory, and black hole thermodynamics enter the picture, that endless capacity starts to look suspicious. Physical reality may not allow unlimited information density. This is where ideas like the Bekenstein bound enter the story. Very roughly speaking, the Bekenstein bound places a limit on the amount of information, or entropy, that can be contained within a finite region of space with finite energy. Again, the important point is not the exact formula tonight. It is the philosophical consequence. There may be a hard limit to how much distinguishable structure can physically fit in a region. That is a stunning thought. It means reality may not have room for infinite detail after all. It means that if you try to cram too much information into too small a space, gravity intervenes. The system collapses toward black hole formation. Nature refuses the overload. In that sense, black holes are not only monsters of gravity. They are guardians of informational limits. They tell us that the universe is not infinitely permissive. There are boundaries to how much can be stored, measured, and meaningfully distinguished. And once you accept that, the idea of a resolution limit no longer sounds strange. It begins to sound almost inevitable. Because if there is a maximum amount of information that can fit into a region, then that region cannot support arbitrarily fine independent detail. Somewhere beneath the smoothness, there must be a finite count of physically meaningful degrees of freedom, not necessarily pixels in the crude visual sense, but a finite informational structure, a deepest granularity in what can be real, distinct, and measurable. This is where the story becomes both more abstract and more powerful. We began by asking whether space might be made of tiny pieces. Now the question is beginning to shift. Maybe the deepest grain of reality is not grain of matter, or even grain of geometry in the simple visual sense. Maybe it is grain of information. Maybe the universe is fundamentally finite in how much it can differentiate, encode, and contain within any bounded region. That possibility transforms the old picture of a continuous cosmos. Instead of infinite smoothness, we get bounded richness. Instead of unlimited divisibility, we get a structured limit. Instead of an endlessly refinable background, we get something more like a physical code with a maximum density. There is a quiet elegance in that. It suggests that reality is not only made of law, but of restraint. The universe is not just what is possible. It is what is possible under limits. Limits of speed, limits of action, limits of energy, limits of resolution, limits of information. And those limits may be the reason the world has a coherent shape at all. Now, if a pixel-like reality had observable consequences, what might they look like? One possibility is that extremely high-energy particles or photons traveling across immense cosmic distances might accumulate tiny effects from the graininess of spacetime. Perhaps their travel times would differ very slightly from what smooth spacetime predicts. Perhaps distant images would blur in characteristic ways. Perhaps the propagation of light at fantastically small scales would reveal some subtle departure from perfect continuity. Physicists have looked for such signs. So far, the universe has been conservative, smooth enough, at least in the tests we can currently perform, to keep its deepest secrets hidden. No definitive evidence of spacetime graininess has appeared, but the search itself is revealing, because it shows what kinds of consequences scientists think a finite resolution universe might produce. Another place to look is in black holes and the early universe, where the density of energy and curvature become so extreme that underlying limits may matter more openly. The behavior of horizons, the fate of information, the structure of the beginning, all of these are places where a finite informational reality may leave fingerprints. And perhaps the most profound consequence is not observational yet, but conceptual. If the universe has a finite information capacity in any bounded region, then our entire metaphysical picture of reality changes. We stop imagining the cosmos as infinitely writable. We stop assuming there is always more room for detail beneath detail beneath detail forever. We begin to see physical reality as something structured, constrained, encoded, and in some deep sense countable. Not countable by us in practice, not with any human technology, but finite in principle. This does not make the universe small. It makes it precise. And it may help explain why mathematics, information, and geometry increasingly seem to overlap at the deepest levels of physics. The old divisions start to blur. A surface becomes a store of information. Entropy becomes geometry. Gravity becomes tied to information flow. Space itself begins to resemble a kind of informational architecture rather than a passive emptiness. There is something deeply calming in that, if you let the idea soften rather than harden, because it means reality is not a formless abyss. It has hidden order, hidden economy, hidden limits that are not arbitrary, but woven into its deepest structure. Even the strangest ideas in modern physics, black hole entropy, holography, informational bounds, all point toward a universe that is more disciplined than it first appears. The smooth sky above us may hide a finite code beneath its silence. The darkness between stars may not be infinite blankness, but lawful depth. A region of space may not be an open container for unlimited detail. It may be a finite and elegant domain, shaped by what the universe permits it to contain. And that brings us back to our original question in a slightly transformed way. If reality is pixelated, we may not notice pixels directly. What we may notice instead are limits. Limits on detail. Limits on measurement. Limits on information. Limits on how much the world can be resolved before the old language of continuity no longer applies. The clue may not look like a visible grid. It may look like a boundary in the laws themselves. And perhaps that is the most beautiful kind of clue. Not a flashing sign, but a quiet refusal. A point where nature says no further in exactly the same way, every time, for reasons rooted in its deepest logic. As we come to the end of this part, let the image settle. Imagine the universe not as a smooth, endless canvas with infinite room for finer and finer detail, but as something with a final depth of resolution. Not visible to ordinary sight, but present in the limits of black holes, in the entropy of horizons, in the finite information that a region can contain. A cosmos whose deepest truth may not be volume, but boundary. Not unbounded detail, but structured finiteness. Not infinite smoothness, but lawful resolution. And if that is true, then one more question naturally waits for us. If the universe has informational limits, if surfaces can encode volumes, if reality itself begins to resemble an elegant code, then how far can that idea go? Could the universe, in any serious sense, be like a simulation? Or is that the wrong question entirely? That is where the next part of our journey leads. If this part helped you settle a little deeper into the mystery, you can subscribe for more slow explorations like this, and if you want, tell me in the comments which idea feels stranger to you, that black holes store entropy on their surface, or that space itself may have a maximum information density. Could reality be like a simulation? There is a certain kind of question that does not arrive all at once. It begins as a joke, perhaps, or as a strange late-night thought, or as a line from science fiction that lingers a little longer than expected. It seems playful at first, almost too modern to be serious. And yet, the more you sit with it, the more it begins to brush against real philosophy, real physics, real uncertainty. What if the universe is not exactly what it seems? What if the smooth world we experience, stars, distance, matter, time, motion, is not the deepest layer of reality, but an emergent surface of something else? Something structured, something encoded, something running according to deeper rules. And from there, almost inevitably, the question appears: could reality be like a simulation? Now, before we go any further, it helps to slow that question down, because the word simulation can mislead us very quickly. For most people, it brings to mind a computer game, a digital world inside a machine, artificial characters moving through coded space. It suggests keyboards, processors, servers, maybe even some hidden external beings watching from outside. And while that imagery is vivid, it is also simplistic. It turns a difficult philosophical and physical question into a piece of pop culture almost too fast. So let us be careful. In this part of our journey, we are not going to treat the simulation idea as a conspiracy, or as a dramatic claim that physicists have secretly proved life is fake. They have not. We are not going to confuse metaphor with evidence. And we are not going to drift into sensationalism. What we are going to do instead is something quieter, and I think more interesting. We are going to ask why the simulation idea appears at all once people start thinking seriously about information, computation, limits of resolution, and the deep structure of spacetime. We will explore what the idea gets right, what it gets wrong, why it attracts both philosophers and physicists, and why, even if the universe is not literally a simulation, the question still tells us something important about the nature of reality. And if these slow explorations into the edges of science help you unwind, you can subscribe, leave a like, or tell me in the comments what feels stranger to you: the idea that reality has a hidden resolution limit, or the idea that the universe might be more like an encoded process than a purely material stage. To begin, let us ask a simpler question. Why does the simulation idea feel plausible at all? A few centuries ago, it would not have felt plausible. Human beings did not live inside worlds of screens, software, rendering, and virtual environments. The metaphor would have had no grip. But now, we are surrounded by systems that generate convincing appearances from underlying code. A game engine can create landscapes, lighting, motion, weather, even the impression of depth and continuity, all from rules and computational updates. So when modern people hear that physics may contain discrete scales, informational limits, and hidden rules beneath visible reality, it is almost natural to reach for the computational metaphor. If images have pixels, maybe space has pixels. If simulations update frame by frame, maybe time has a smallest tick. If code generates virtual worlds, maybe physical law generates ours in a similar way. That is the emotional logic of the idea. And there is something understandable about it. It is a metaphor born from the tools of our age. But metaphors are useful only if we know where they stop. A rendered world inside a human computer is one particular kind of rule-based system. The universe, if it has a deeper rule-based structure, is not obliged to resemble our machines simply because our machines are the best analogy we happen to have. A bird is not an airplane. An atom is not a solar system. A field is not a fabric in the literal sense. In science, metaphors help us cross the first bridge, but they are not the destination. So when we ask whether the universe is like a simulation, the most useful word in that sentence may be like. Like a simulation in what sense? Like one because it may have finite resolution? Like one because complex appearances may emerge from simpler rules? Like one because information might be more fundamental than matter in some contexts? Like one because what looks continuous may arise from something discrete? Those are serious questions. And none of them require us to believe that someone, somewhere, is sitting outside the universe at a cosmic desk. Now, one of the most famous philosophical versions of the simulation idea came from Nick Bostrom's simulation argument. The argument is often misunderstood, so it helps to state its mood carefully. It is not a proof that we are in a simulation. It is a philosophical trilemma. Very roughly, it says that at least one of three things must be true. Either civilizations rarely survive long enough to develop the ability to run vast numbers of ancestor simulations, or advanced civilizations rarely choose to run them, or if many such simulations are run, then simulated conscious beings may vastly outnumber non-simulated ones, making it statistically plausible that we ourselves are simulated. Whether one finds that argument compelling or not, it is not really a physics argument. It is a reasoning exercise about probability, technology, and consciousness. Its power lies in how it destabilizes intuition. It makes people realize that once simulated worlds become conceptually possible, the simple confidence that we must be in the base layer of reality becomes harder to justify by instinct alone. But physics asks a different question. Not, what is statistically possible in some abstract future of civilization, but what features of our universe would suggest a deeper computational or informational structure? That is a much harder question. Because physics needs actual constraints, actual observables, actual law. And this is where the simulation metaphor becomes both interesting and dangerous. It becomes interesting because many ideas in modern physics do, in fact, suggest limits, discreteness, and rule-like structure. We have already seen some of them. The Planck scale hints at a smallest meaningful length and time. Quantum theory teaches us that nature already quantizes many things. Black hole thermodynamics suggests informational limits. Some approaches to quantum gravity describe spacetime as emergent from more primitive structure. Computational views imagine reality unfolding through updates. All of this can make the universe feel less like a smooth classical stage and more like something generated from deeper laws. But the metaphor becomes dangerous when people jump from generated to programmed, and from programmed to artificial, and from artificial to fake. Those leaps are not justified. A snowflake is generated by physical law. That does not make it fake. A crystal is structured by rule. That does not make it unreal. A galaxy forms according to deep equations. That does not make it a deception. The fact that reality may arise from hidden structure does not downgrade reality. It only changes how we describe its foundation. That point matters deeply. Because many people hear the simulation idea and take from it an emotional message that does not follow. They imagine that if the universe has code-like properties, then their life must be less real, less meaningful, less solid. But that does not follow at all. Even if the deepest layer of reality were informational, relational, or computational in some way, your experience, your thoughts, your loves, your losses, your nights, your memories, would still be real as experiences within that structure. Emergence does not mean falseness. It means dependence on a deeper layer. That is a more mature way to hold the question. Now, there are certain reasons physicists have occasionally entertained simulation-like language more seriously than one might expect. One reason is efficiency. In computer graphics, simulations often do not render every possible detail at once. They use shortcuts, symmetries, resolution limits, local updating, information constraints. In a very loose way, some features of physics, especially finite speeds of influence, quantum indeterminacy, and informational bounds, can make people wonder whether reality also behaves with a kind of deep economy. Not because it is a designed simulation, necessarily, but because lawful systems often find elegant ways to limit what must be specified. Another reason is discreteness. A truly continuous universe contains difficult infinities. Quantum gravity research often stumbles upon the suspicion that continuity may fail at the smallest scales. A discrete underlying structure feels, to many minds, more manageable, more countable, more code-like. Again, that does not prove simulation. It simply makes the analogy tempting. A third reason is the rise of information as a foundational concept. When black holes seem to store entropy on surfaces, when quantum theory increasingly resembles a theory of possible information, when geometry and information begin to intertwine, it is not surprising that people begin to ask whether physical reality is, in some deep sense, informational at its base. And that question is very close to the heart of the simulation metaphor. Not because information automatically means software, but because it shifts reality away from the old picture of matter as tiny little lumps in empty space, and towards something more abstract: relations, states, constraints, transformations, encodings. Now, if one wanted to look for evidence that the universe is literally simulation-like, what would one even search for? This is where many proposals become speculative very quickly. Some have suggested that if spacetime were discretized in a lattice-like way, extremely high-energy particles might reveal directional anomalies, as though there were a hidden underlying grid. Others have wondered whether physical constants might show signs of optimization or computational economy. Some have speculated about glitches, irregularities, or boundaries in cosmic behavior. But here, science must remain disciplined. The universe has not given us any convincing sign that it is literally a human-style simulation. No discovered glitch. No external processor hum. No evidence of an artificial boundary beyond which the rendering fails. These ideas make for good fiction, but they are not established physics. In fact, many physicists are cautious or skeptical of the entire framing, because it often adds another layer of speculation without increasing explanatory power. If you say the universe is simulated, a natural question follows: simulated in what? By what laws? Running on what substrate? In what larger reality? And then the original mystery simply moves outward one level. You have not explained law. You have relocated it. That does not make the question worthless, but it does reveal one of its limits. The simulation idea can sometimes feel explanatory when it is really only metaphorical. Still, there is a more serious version of the question hiding underneath all the noise. Not, is the universe fake? But, is the universe fundamentally emergent from a lower-level rule system? That is a much better question, because it does not assume servers, designers, or external beings. It only asks whether visible reality may arise from deeper formal structure. And in that form, the question overlaps with several real programs in theoretical physics. Loop quantum gravity asks whether smooth geometry emerges from quantized structure. Causal approaches ask whether spacetime grows from order relations between events. Computational approaches ask whether simple update rules can generate relativistic and quantum-like behavior. Holographic ideas ask whether volumes emerge from boundary information. None of these theories is simply the simulation hypothesis, but all of them share a family resemblance with it. They suggest that what we experience may not be the final layer. That reality may have a grammar beneath its appearance. Now, there is also a philosophical caution worth keeping close. If reality is generated from deeper rules, that does not mean those rules are simple in the way a toy simulation is simple. Nature may be far stranger than any digital world we build. Our simulations rely on external time, external hardware, external designers, external mathematical frameworks. A fundamental physical reality, whatever it is, cannot assume those external supports in the same way. It must account for time, causality, energy, and law from within itself. That is why analogies to software often break under pressure. A game engine runs in ordinary time on a physical device. The universe, as far as we know, does not have the luxury of a background clock outside itself. It is the total physical system we are trying to describe. So if there is some deep rule-like structure, it is not software in the ordinary human sense. It is something more basic and harder to picture. And yet the metaphor remains useful for one reason. It reminds us that appearance and foundation need not match. A rendered world can look smooth while being built from discrete operations. A three-dimensional image can emerge from two-dimensional encoding. A richly detailed environment can follow from simple update rules. All of those ideas echo, in very loose but provocative ways, the lessons modern physics has already been teaching us. So perhaps the healthiest response to the simulation question is neither belief nor dismissal. Perhaps it is refinement. Not, yes, reality is definitely a simulation. Not, no, the question is silly. But rather, the question is clumsy, yet it points toward something real. It points toward the possibility that the universe is not fundamentally what naive intuition says it is. That smoothness may emerge from structure. That information may matter as much as material substance. That boundaries, resolution limits, and rule-based order may belong deep in the architecture of things. And in that sense, the simulation metaphor can serve as a doorway, provided we do not mistake the doorway for the room. There is also a quiet emotional lesson here. The simulation idea can make some people uneasy because it seems to threaten the authenticity of life. If this is all generated, they think, then maybe it is not real. But this fear rests on a false contrast. A song generated by vibrating strings is still a real song. A storm generated by atmospheric law is still a real storm. A mind emerging from biological processes is still a real mind. Emergence does not cancel reality. It describes how reality is organized. So even if the deepest layer of the cosmos turned out to be something informational, relational, or process-based, your existence would not become lesser. It would become more layered. And that, to me, is the calmer way to hold the mystery. Not as a threat, as a deepening. The world remains the world. Stars burn. Time passes. Breath rises and falls. Love matters. Loss matters. Meaning matters. Physics does not erase those things by showing that they rest on hidden law. If anything, it enlarges them by revealing how much unseen structure supports the ordinary. Now, as this part draws toward its close, we can see the simulation question for what it really is. At its shallowest, it is a modern myth dressed in digital imagery. At its deepest, it is a rough modern way of asking an ancient question. Is appearance fundamental, or does it arise from something deeper? That ancient question remains fully alive. And physics, in its own careful way, keeps nudging us toward the possibility that what appears smooth, solid, and continuous may indeed emerge from a hidden layer of rules, relations, limits, and information. Whether that deserves the name simulation is another matter. Perhaps it does not. Perhaps the better word is simply structure, or process, or law, or grammar. Whichever word we choose, the deeper point remains. Reality may not be the final thing it appears to be. There may be a source code of sorts, though not necessarily code written by hands. There may be an underlying order from which spacetime, matter, and experience arise. And if that is so, then the most important question is not whether the universe is fake. It is what kind of reality can give rise to one like this. That is the better wonder. And it leads naturally to the final step in our journey. Because after Planck lengths and Planck times, quantum packets and restless vacuums, quantum weaves, generative processes, informational limits, and simulation-like metaphors, we are left with the quietest and biggest question of all. What would it mean, really, if reality is not smooth but built from tiny pieces? How should that change the way we see the universe, and ourselves within it? That is where the final part takes us. If this helped you settle into the mystery a little more deeply tonight, you can subscribe for more slow explorations like this, and if you want, tell me in the comments whether the word simulation helps you think about reality, or only makes the mystery feel stranger. If reality is built from tiny pieces, by now, the question that first seemed strange has started to feel almost familiar. Not fully comfortable, not ordinary, but familiar in the way a distant mountain becomes familiar after you have spent enough time looking at it in changing light. At first it was only a shape on the horizon. Then details appeared. Ridges, shadows, contours. What once felt abstract now feels inhabited. We began with a simple but unsettling possibility. What if space and time are not smooth? What if the universe, beneath all the graceful continuity we seem to experience, is built from tiny indivisible pieces. At the beginning, that idea may have sounded like a poetic exaggeration, or perhaps like a piece of science fiction. But as we moved slowly through the clues, one by one, it became harder to dismiss. The Planck length suggested a smallest meaningful scale of distance. The Planck time suggested a smallest meaningful interval of duration. Quantum theory revealed that nature already likes packets, jumps, and allowed values. The vacuum turned out not to be empty. Geometry itself began to look unstable at the deepest scales. Some theories suggested a hidden weave of space. Others suggested an underlying process. Others still implied that the universe may have informational limits, a finite depth of resolution, perhaps even something like a hidden code beneath its smooth appearance. And now, after all of that, we arrive at the quietest and perhaps most important part of the journey. What does it mean? Not only for physics, for how we imagine reality at all. Because sometimes a scientific idea does more than solve a technical problem. Sometimes it changes the shape of the world and the mind. It alters the emotional feel of existence. Not by making life less real, but by showing that reality is layered more deeply than ordinary intuition ever guessed. So in this final part, we are not racing towards some false certainty. We are not pretending that science has already settled the question. It has not. No one has yet proved that spacetime is truly discrete. No final theory has closed the case. The puzzle remains open. But even without final proof, the possibility itself has already taught us something powerful. It has taught us that reality may not be what first appears. And if these slow, calm journeys through the deepest questions of science help you rest a little more easily, you can subscribe, leave a like, or tell me in the comments which idea stayed with you most through this whole journey. The smallest length, the smallest moment, quantum foam, atoms of space, the universe as process. Any of them. To begin, let us return to the oldest instinct we have been gently questioning all along. The instinct that the world is smooth. It is an understandable instinct. We live in the scale of flowing things. Water pours. Wind moves. A hand crosses a table in one continuous motion. A melody unfolds through time. A sunrise brightens the sky by degrees. Nothing in ordinary life forces us to believe in hidden steps underneath. The world is generous enough at our scale to feel seamless. And in a way, it truly is seamless, for us. That part matters. When physics questions smoothness, it is not saying that experience is false. It is saying that experience may be emergent. The continuity we live inside may be real at our level, just as temperature is real, just as a rainbow is real, just as a coastline is real from an airplane even though it dissolves into detail when approached differently. Emergence is not deception. It is layered truth. The smooth universe we experience may be exactly what a deep discrete universe looks like when viewed from the human scale. That is one of the most important things to understand. If space and time do come in tiny pieces, that does not mean the world suddenly becomes jagged, mechanical, or visibly pixelated like an old screen. The possible granularity lies so far beneath ordinary measurement that continuity would still reign in daily life. The moon would still rise softly. Oceans would still move in long curves. Thought would still feel like thought. The human world would remain whole. But underneath that wholeness, there may be a hidden architecture. And once you let yourself imagine that, reality changes shape in a subtle and beautiful way. Because a smooth universe and a built universe do not feel emotionally identical. A smooth universe feels like an endless canvas. A built universe feels like an intricate composition. A smooth universe suggests infinite divisibility, endless refinement, perhaps even a kind of quiet blankness beneath things. A built universe suggests law, structure, decision, relation, perhaps even economy. Not economy in the human financial sense, but in the deep physical sense that the world is not wasteful. It has boundaries, limits, patterns. hidden forms of organization. That changes not only how we think about matter and space, but also how we think about mystery. In an older worldview, mystery often meant distance. The stars are mysterious because they are far away. The universe is mysterious because it is vast. But this journey has revealed another kind of mystery. Mystery through depth. Not far away, but beneath. Not out there, but under the familiar. The room around you may already contain it. The silence between sounds. The interval between moments. The empty-looking space above your bed or ceiling or window. All of it may rest upon a foundation more intricate than sight can ever directly reveal. That is a strangely comforting thought, because it means the ordinary world is not ordinary all the way down. Now, one way to hold this whole journey together is to notice a pattern. Again and again, physics has discovered that what seems continuous often is not fundamental. Matter once looked solid and smooth. It became atoms, then subatomic structure, then fields and quantum states. Light once looked like a continuous wave. Then it revealed photons. Atomic energy levels once seemed as though they should vary freely. Then they became quantized. Empty space once looked like nothing. Then it became a restless vacuum. Spacetime once looked like a calm continuum. Then the Planck scale appeared, and with it, the possibility that geometry itself may have a hidden grain. The pattern is not proof, but it is suggestive. Nature keeps inviting us to look beneath smooth appearance and find deeper structure. So if space and time are built from tiny pieces, they would not stand alone as a bizarre exception. They would be part of a larger lesson the universe has already been teaching for more than a century. The lesson that continuity is often a surface phenomenon. That law can be granular underneath. That smoothness may be the shadow of a deeper order. Now let us be honest again, because honesty is part of what makes this calm rather than dramatic. We do not know the final answer. It is still possible that spacetime is continuous in some subtle way, and that the Planck scale marks not discrete building blocks but only a breakdown of our current theories. It is possible that continuity survives, but in a form very unlike the old classical picture. It is possible that neither smooth nor pixelated is quite right, and that the deepest structure of reality belongs to a category our ordinary language does not yet capture. That is not disappointing. That is science at its most alive. The best questions do not always end in immediate closure. Sometimes they widen the mind first. Sometimes they refine our imagination before they resolve our equations. Sometimes the value lies in discovering that the old categories were too small. And this question has certainly done that. Because whether reality is literally discrete or not, the journey has already forced us to abandon a simpler worldview. A worldview in which space is passive, time is obvious, emptiness is empty, and continuity is guaranteed. That older world is gone. In its place stands something richer. A universe where distance may have limits. Where time may have a smallest meaningful pulse. Where the vacuum may shimmer. Where geometry may be quantized. Where information may shape physical law. Where what appears smooth may emerge from something granular, relational, or process-like underneath. That is already enough to make the cosmos feel transformed. And perhaps this is where the human side of the question quietly returns. Because after all the deep theory, all the scales too small to imagine, all the abstractions about quanta and geometry and information, we are still left with ourselves. Small conscious beings, awake for a while inside a reality we did not design, trying to understand what kind of place, or process, or structure we inhabit. There is something very moving about that. That creatures made of atoms on one small world around one ordinary star can ask whether space itself has atoms. That minds built from biology can wonder whether time has a smallest tick. That beings who live in the middle scale, neither cosmic nor Planck-sized, can still sense that the familiar world may rest on invisible principles of astonishing depth. In that sense, the question is not only about physics. It is about the reach of curiosity. And curiosity, when it is calm enough, can feel almost like a kind of peace. Not the peace of having all the answers. The peace of realizing that reality is more beautiful than the first answer. Now, if the universe truly is built from tiny pieces, then one consequence is especially worth dwelling on. It means that infinity may not belong to physical detail in the way we once assumed. The world may be finite in its resolution, finite in the information a region can contain, finite in the smallest meaningful scales of space and time. Infinity would then remain a powerful mathematical idea, but physical reality itself may be more disciplined, more bounded, more elegantly constrained than classical imagination suggested. That is not a loss. It is a different kind of grandeur. An ocean does not need to be infinite to be beautiful. A piece of music does not need endless notes to be profound. A night sky does not need boundless divisibility to inspire wonder. Sometimes form is more astonishing than formlessness. Sometimes limits are what allow a thing to have character at all. A universe built from tiny pieces would not be a lesser universe. It would be a universe with grammar. And grammar is one of the reasons anything meaningful can appear. At the same time, if reality is built from tiny pieces, then smoothness itself becomes one of the universe's great artistic achievements. Because out of discrete foundations would emerge continuity, motion, warmth, gravity, memory, thought, and sleep. Out of the deepest grain would come the soft world we know. That is almost poetic. That the roughest level may give rise to the gentlest appearances. That beneath every smooth horizon there may be hidden architecture. That the world feels fluid not because it is simple, but because its complexity is too fine for us to see directly. And perhaps that is why this idea lingers so powerfully in the mind. It is not only intellectually strange, it is aesthetically strange. It asks us to imagine a universe whose deepest layer is not visible, not tactile, not intuitive, and yet whose large-scale expression is everything beautiful and familiar to us. A cosmos in which the moonlit sky and the grain of spacetime are not opposites, but two scales of the same reality. Now, as we settle toward the end of this long journey, there is one final balance worth keeping: wonder and restraint. Wonder, because the possibility is extraordinary. Restraint, because possibility is not proof. Science moves best when it keeps both. Too little wonder, and the mind never dares the deeper question. Too little restraint, and mystery becomes fantasy. The healthiest place lies between them. Curious, but disciplined. Open, but careful. Ready to imagine, but willing to wait. And that is where we must leave the question. Not solved forever, but alive. Alive in black hole physics. Alive in quantum gravity. Alive in every attempt to reconcile relativity with quantum theory. Alive in the possibility that information, geometry, and law may be far more tightly woven than we yet understand. The final answer may come slowly, through mathematics, through experiment, through ideas not yet invented. Or it may arrive in a form stranger than anything we have guessed tonight. But even now, before the answer, the question has already done its work. It has made the universe feel deeper. It has made the small feel as profound as the large. It has reminded us that reality is not exhausted by appearance. And perhaps most of all, it has given us a new way to look at the world as we drift toward rest. Not as a blank continuous stage, but as something that may be finely made, exquisitely made. Made of tiny pieces, or of limits, or of relations, or of hidden structure so delicate that all of ordinary existence rises from it like a dream from a sleeping mind. So tonight, as the mind grows quieter, you might let the question settle without forcing it to conclude. Maybe space is smooth. Maybe it is woven. Maybe time flows. Maybe it ticks. Maybe the universe is continuous. Maybe it is built. Maybe reality is a perfect seamless fabric. Or maybe it is a masterpiece so finely stitched that no ordinary eye can see the thread. Either way, we live inside something extraordinary. A cosmos vast enough to contain galaxies, and subtle enough to hide its deepest structure beneath the appearance of simplicity. A reality that may be both softer and stranger than we first believed. And perhaps that is enough for now. Not certainty. Just the feeling that the universe, all around you and all beneath you, is deeper than it looks. If this journey helped you relax, think, or drift off a little more peacefully, you can subscribe for more slow explorations like this one. And if you feel like leaving one last thought in the comments, I'd love to know which possibility you find more beautiful, that reality is perfectly smooth, or that it is built from tiny hidden pieces. Either answer opens into wonder.